There are places in the universe so empty, so vast, that calling them nothing barely captures their scale. Imagine a region hundreds of millions of light years across, a cosmic desert where entire clusters of galaxies could fit side by side, yet only a handful exist. This is the Boötes void, a structure so enormous that when astronomers first discovered it, they thought it had to be a mistake. It's a hole in the fabric of the cosmos, an absence so large it redefines what we mean by emptiness. But this emptiness is not meaningless. The Boötes void is a window into how the universe grew, how gravity sculpted galaxies into thin filaments, leaving behind immense cosmic chasms. A universe woven from nothingness. When astronomers map the universe on the grandest scales, they don't find a uniform sea of galaxies stretching evenly in all directions. Instead, what they uncover looks more like a colossal web, a network of delicate filaments made of galaxies, stretching across billions of light years. Between these threads lie vast regions of emptiness, dark voids that span hundreds of millions of light years across, where almost nothing exists at all. It's a breathtaking sight, and also a puzzling one. How did a universe that began in a near perfectly smooth explosion come to look so uneven, so intricately structured? From a distance, the cosmic web resembles veins of light spread across a dark canvas. Each glowing point is not a single star, but an entire galaxy, sometimes billions of them, drawn together by gravity into long, thin strands. Where these strands intersect, galaxy clusters form, like knots in a tangled string. The largest of these clusters can contain thousands of galaxies, immense clouds of hot gas and invisible halos of dark matter that extend far beyond what we can see. Between these dense intersections are the cosmic voids, enormous expanses almost completely empty of galaxies. The average density inside these voids can be less than 1/10 of the cosmic average, making them the loneliest places in the known universe. This strange pattern didn't exist in the early universe. When the cosmos was young, just hundreds of thousands of years after the Big Bang, it was a glowing fog of hydrogen and helium gas, nearly uniform in every direction. The differences in density were tiny, no more than 1 part in 100,000. But these small ripples were the seeds from which everything we see today would grow. Over billions of years, gravity began to magnify those tiny differences. Slightly denser regions pulled in more matter, becoming denser still. The less dense regions gave up their material to the growing clumps, creating an ever sharper contrast between structure and emptiness. What began as faint ripples in the fabric of the early universe gradually turned into filaments, clusters, and voids. Gravity worked as the cosmic weaver, pulling invisible threads together and leaving behind patches of emptiness. It's a slow and relentless process, one that took billions of years to sculpt the universe into the shape we now observe. Computer simulations have recreated this evolution in remarkable detail. Scientists feed in the physics of the Big Bang and the laws of gravity, and after billions of simulated years, what emerges is a digital version of the same cosmic web that telescopes see in the real universe. The match is stunning, a clear sign that gravity alone, acting on the matter formed after the Big Bang, can create the large-scale pattern of structure and emptiness we observe today. But this web is not woven from ordinary matter alone. In fact, most of the universe's structure is built upon something we cannot see, dark matter. Though invisible, it exerts gravity just like normal matter, guiding the formation of galaxies and clusters. It acts as the scaffolding of the cosmos. Ordinary matter, the atoms that make up stars, planets, and people, simply follows the invisible framework laid out by dark matter. As it cools and collapses along these dark filaments, it ignites into galaxies and stars, tracing the same structure that dark matter carved into space. In this sense, what we see through our telescopes is only the glowing outline of a much deeper, unseen pattern. The first hints of this cosmic web came in the 1980s, when astronomers began mapping the positions of galaxies in 3 dimensions. Instead of a random scatter, the data revealed an intricate structure, long chains and walls of galaxies forming boundaries around immense voids. On the largest scales, the cosmic web stretches across the observable universe like a living organism. The filaments connect clusters of galaxies like nerves and blood vessels, connecting organs. Some astronomers have even compared it to the structure of a brain, where galaxies act as neurons in a vast cosmic network. Of course, this is only an analogy, but it demonstrates the awe the cosmic web inspires. It is a structure both grand and delicate, a universe woven from almost nothing, shaped by forces invisible to the eye. When we peer into these filaments, we find that they are far from simple threads. Each filament is a corridor of activity, where galaxies collide, merge and evolve. Streams of hot gas flow along them, feeding clusters at their intersections. Supermassive black holes at the centers of galaxies inject energy back into this environment, heating and stirring the gas, slowing down new star formation. The web, in this way, is not a static structure, but a dynamic, evolving ecosystem. Over billions of years, gravity, radiation, and cosmic expansion all interact within it, constantly reshaping the balance between structure and void. The voids themselves are just as fascinating. Though nearly empty, they still hold traces of matter, faint wisps of gas and stray galaxies that drift through their darkness. These galaxies tend to be small and dim, isolated from the gravitational pull of larger structures. Life inside a cosmic void would be extraordinarily lonely. The nearest bright galaxy could be hundreds of millions of light years away. Yet these voids are important clues to understanding how the universe expands. Because they are less affected by gravity, they allow scientists to measure cosmic expansion more cleanly than dense regions do. In a way, the emptiness helps reveal the invisible hand of dark energy, the mysterious force driving the universe to expand faster over time. Everywhere we look, the contrast between structure and emptiness tells a story. The cosmic web shows how gravity sculpts the universe into patterns of light and dark, matter and void. Without voids, there would be no place for the filaments to stretch. Without gravity's pull, there would be no structure to define the emptiness. The two exist in balance, each giving meaning to the other. As telescopes grow more powerful, we continue to map this cosmic architecture in greater detail. The Sloan Digital Sky Survey and the Dark Energy Spectroscopic Instrument, or DESI, have created some of the most detailed 3D maps of the universe ever made, showing billions of galaxies spread out across space. These maps allow scientists to trace the web's structure across cosmic time, to see how it has grown and changed over billions of years. And even with all this knowledge, the sight remains humbling. The cosmic web may look delicate, but it is made of the same matter that formed stars, worlds, and life itself. It is both a grand design and a simple consequence of gravity acting on matter. When we look at this immense network, we are seeing the universe's largest pattern, a masterpiece of cosmic evolution. And though we may only see a small part of it from our tiny world, we are part of that same web. Strands of matter and energy, connected to the whole by the quiet, patient pull of gravity that has been weaving the universe since time began. The first maps of the cosmic web. For most of human history, the universe appeared as a simple and orderly place. Even when astronomers began to realize that the faint smudges of light in their telescopes were entire galaxies, they still assumed those galaxies must be evenly spread throughout the cosmos. There was no reason to think otherwise. The night sky looked uniform, calm, and infinite, a quiet ocean of light stretching without pattern or edge. But that comforting image began to unravel in the second half of the 20th century, when astronomers started to look not just at where galaxies appeared on the sky, but how far away they were. This was the birth of redshift surveys, the first true three-dimensional maps of the universe. To understand how they worked, imagine looking at a city skyline. From a distance, all the buildings seem to lie on a flat line, their heights and distances indistinguishable. But once you begin to measure how far each building stands from you, the flat image turns into a landscape with depth. Astronomers wanted to do the same with the universe, turn their flat maps of galaxy positions into a full 3D picture of where everything actually was. The key to this was redshift. When light travels from a galaxy that's moving away from us, its wavelength stretches, becoming redder. The faster the galaxy moves away, the more its light is shifted toward the red end of the spectrum. Since the universe is expanding, a galaxy's redshift can be used as a kind of cosmic distance marker. The greater the redshift, the farther away the galaxy lies. By measuring redshifts for thousands of galaxies, astronomers could begin to build the first real maps of space. In the 1970s, these efforts were still limited by technology. Measuring redshifts required careful observation through spectroscopes, and every galaxy took time. It was slow, painstaking work, but it carried the promise of revealing something no one had ever seen: the true structure of the universe. The first major breakthroughs came in the 1980s, with surveys conducted by teams such as those led by Margaret Geller and John Huchra at the Harvard-Smithsonian Center for Astrophysics. Using improved instruments and more powerful computers, they began to map the positions and distances of thousands of galaxies across large sections of the sky. When the data was plotted, instead of a random distribution, the galaxies formed patterns, long chains, arcs, and walls of matter separated by immense voids. The maps looked like cross-sections of a sponge, with dense regions connected by thin threads and vast empty bubbles in between. The uniform universe that astronomers had long imagined simply did not exist. It was structured, the first visual evidence of what would later be called the cosmic web. One of the most striking discoveries was the Great Wall, an enormous chain of galaxy clusters stretching more than 500 million light-years in length. It was one of the largest structures ever detected in the universe, and it defied expectations. No one had imagined galaxies could organize themselves on such enormous scales. The Great Wall was like a boundary between light and darkness, a luminous ridge marking the edge of a cosmic void hundreds of millions of light-years wide. When the discovery was first presented, it sent ripples through the scientific community. Suddenly, the word structure had a new meaning when applied to the cosmos. To grasp the scale of this revelation, it's important to remember how the idea of empty space had been understood before. Astronomers once thought that between galaxies there was simply nothing, a true vacuum stretching endlessly between points of light. But the first redshift surveys showed that these empty regions weren't random gaps. They were vast voids, part of a larger geometric pattern. How could such massive patterns have formed? The galaxies in these maps weren't isolated points. They were part of an interconnected system, shaped by forces acting across hundreds of millions of light-years. The answer began to emerge from cosmological simulations, which modeled how matter would behave under gravity over billions of years. Starting from the tiny fluctuations seen in the cosmic microwave background, the faint afterglow of the Big Bang, these simulations predicted that matter would naturally clump together into filaments, leaving behind the enormous voids. When astronomers compared these predictions with the actual maps from redshift surveys, the resemblance was uncanny. Nature had followed the same laws of physics that computers had simulated. As redshift surveys expanded, the maps grew more detailed and more surprising. The Las Campanas redshift survey in the 1990s pushed the boundaries further, charting over 25,000 galaxies. Then came the Sloan Digital Sky Survey, or SDSS, in the early 2000s, which used a dedicated telescope in New Mexico to measure millions of galaxies with precision never before possible. The Sloan maps revealed the cosmic web on an unprecedented scale, not as a handful of clusters and walls, but as an interconnected network stretching across the entire observable universe. The patterns seen in these surveys also changed how scientists thought about dark matter. Ordinary matter alone couldn't explain the size and coherence of the filaments and walls. There simply wasn't enough visible matter to create such immense structures by gravity alone. Something unseen had to be there. Something providing the gravitational framework upon which galaxies gathered. The redshift maps, in a way, became a map of dark matter, showing its hidden architecture through the behavior of visible galaxies. Even the voids carried clues about this invisible scaffolding. When astronomers studied how galaxies around the edges of voids moved, they could infer how much unseen mass was pulling or pushing them. The motion of galaxies wasn't random. It followed the contours of the underlying dark matter landscape. This realization marked a profound shift in cosmic thinking. As the maps grew more refined, they began to reflect how structure naturally emerges when small differences are amplified by simple physical rules. Just as small variations in the early universe grew under gravity, small fluctuations in living systems lead to complex forms. The universe, it seemed, was another example of complexity arising from simplicity, a pattern woven by nature itself. The more astronomers mapped, the more they realized that no two parts of the cosmic web were exactly alike. Each region had its own shape, its own local arrangement of clusters and filaments. Some areas contained massive superclusters, while others opened into deep voids. The maps revealed a cosmos that was both predictable in its laws and chaotic in its details. Today, the descendants of those first redshift surveys continue to expand our cosmic view. Instruments like DESI are measuring tens of millions of galaxies, refining the 3D model of the universe down to fine detail. Yet the foundations of this work, the first painstaking redshift measurements from the 1980s, remain some of the most transformative in the history of astronomy. Those early maps marked the moment when humanity stopped seeing the universe as a flat sky and began to perceive its true depth. The galaxies were no longer isolated islands floating in an endless sea. They were the bright knots in an immense invisible fabric. When astronomers found nothing, and it mattered. Astronomers didn't set out to find voids. Their discovery came almost by accident. One of the first such regions to draw attention was the Boötes void, discovered in 1981 by astronomers Robert Kirshner and his colleagues. It was a patch of the universe about 330 million light-years across, containing only a few dozen galaxies where thousands were expected. To visualize its scale, if the Milky Way were placed near one edge of this void, the nearest large galaxy would lie hundreds of millions of light-years away, an almost unimaginable emptiness. The team didn't believe it at first. Their instruments were fine, their data solid, but the idea that such a vast stretch of space could be nearly devoid of galaxies seemed impossible. It forced them to question whether their understanding of cosmic structure was incomplete, or perhaps fundamentally wrong. At the time, cosmology was entering a new phase. The discovery of the cosmic microwave background, or CMB, had confirmed the Big Bang model, and most scientists assumed that matter, on the largest scales, was evenly distributed. The presence of enormous voids shattered that assumption. The first reaction was skepticism. Some argued that the apparent emptiness was a statistical illusion caused by limited data. Others thought it might be a local anomaly, an unusual patch of the universe that didn't reflect the bigger picture. But as more surveys came in, the pattern repeated itself. The CFA Redshift survey in the early 1980s, one of the largest of its kind at the time, produced a now famous slice of the universe map. It showed galaxies arranged in long, thin filaments with enormous gaps between them, so large that they dwarfed even the biggest known clusters. The more data astronomers collected, the clearer the structure became. The universe was a sponge-like network. This meant that the simple models of cosmic evolution were missing something crucial. Gravity alone could not easily explain the creation of such large empty regions unless the early universe had already contained slight differences in density. But what caused those density differentials? And why did they leave behind such enormous holes? These questions began to push astronomers toward a deeper understanding of how structure formed after the Big Bang. Voids were soon recognized as more than just empty space. They were active parts of cosmic evolution. Over time, the gravitational pull of the surrounding filaments drained material away from these regions, amplifying their emptiness. In other words, the voids didn't just exist, they grew. As galaxies and dark matter moved toward denser areas, the voids expanded, pushing against one another and shaping the geometry of the cosmic web itself. Even within the largest voids, faint traces of matter lingered, thin wisps of gas, isolated dwarf galaxies, and the ever-present fabric of dark matter. Some studies have found tiny filaments threading through the voids, like delicate veins of structure nearly invisible to telescopes. These hidden strands suggest that even the emptiest parts of the universe are not truly void, but simply less illuminated. The cosmos, rather than being filled with occasional pockets of light, is a continuous fabric in which light only marks the densest regions. The Boötes void became a kind of symbol for this shift in thinking. What began as an odd data point evolved into a cornerstone of modern cosmology. It showed that emptiness was not an exception, but a fundamental feature of the universe. Every galaxy cluster, every filament, owes its existence to the contrasting presence of these vast, evacuated zones. In a sense, the universe builds structure by removing it, by letting certain areas fall silent so that others can grow bright. As computing power improved, simulations helped bring this picture into focus. By recreating the early universe and allowing gravity to act on tiny fluctuations in density, scientists watched virtual matter organize itself into a pattern strikingly similar to what telescopes had revealed. Still, these voids remain among the most mysterious environments in existence. Because they contain so little, they offer some of the cleanest laboratories for studying dark energy and the expansion of the universe. In dense regions, gravity complicates measurements, but in voids, where there is almost nothing to interfere, scientists can more clearly observe how space itself stretches. Some recent studies suggest that the behavior of voids might even reveal whether dark energy changes over time. The emptier the voids grow, the faster the universe seems to accelerate. Astronomers have also started to explore the galaxies that do exist within these vast deserts. These so-called void galaxies tend to be small, isolated, and unusually blue, meaning they're still forming stars, even in their loneliness. Cut off from the dense filaments where galaxies collide and merge, these cosmic hermits evolve slowly, like islands untouched by the chaos of the larger universe. By studying them, scientists can glimpse what galaxies might have been like in the early days of cosmic history, simple, undisturbed, and ancient in their solitude. They are the quiet partners in a cosmic duet, the silent spaces between the notes of creation. When astronomers found nothing, it mattered more than anyone could have expected. For in that nothingness lay the key to understanding how everything else came to be. What makes a void a void? What qualifies as a cosmic void? How empty must a region be before it counts as one? On the surface, this might seem like a simple question, but the answer depends on how you measure it. The universe is filled with matter on many scales, from stars to galaxies, from clusters to superclusters. To define a void, astronomers first calculate the average density of the universe, the total amount of matter, both visible and dark, divided by the space it fills. This average acts as a baseline. A void is then any region where the density falls far below that baseline, often less than a tenth of the cosmic average. In other words, if you could scoop up a typical patch of the universe and compare it to a region inside a void, the void would contain 10 times less matter, sometimes even 100 times less. These measurements aren't made with a single observation. Instead, they're built from vast surveys. By mapping where galaxies cluster and where they do not, scientists can calculate how dense or sparse different regions are. Computer algorithms scan these maps to identify large continuous areas that meet the criteria for underdensity. The result is a catalogue of voids, each with its own shape, size, and degree of emptiness. Voids are not uniform spheres of nothingness. They come in irregular, often sponge-like shapes, molded by the surrounding filaments. Some are nearly round, but others are stretched or twisted, linked together like bubbles in foam. Between them, thin walls of galaxies mark the boundaries, forming the skeleton of the cosmic web. Even within the emptiest of voids, however, the story is not one of total absence. The remaining matter inside these regions tells its own quiet story. Gas still lingers there, though it is so thin that a cubic meter might contain just a few atoms. Dark matter forms a faint ghost-like structure of its own, and scattered throughout are galaxies, not the bright massive spirals that dominate clusters, but smaller, simpler ones, often low in heavy elements and still forming stars. These galaxies are rare, but their presence reminds us that voids are part of the same interconnected web as everything else. Defining a void, then, is not just about counting how many galaxies it lacks, but about understanding the balance between isolation and connection. Astronomers often describe voids by their density contrast, a number that compares the local density to the cosmic mean. A density contrast of 0.9, for instance, means the region contains only 10% of the expected matter. Such regions are considered deep voids. Shallower voids with higher densities are sometimes found near the edges of filaments, where galaxies are sparse but not entirely absent. These gradients of emptiness give scientists clues about how matter has flowed over cosmic time, migrating from the interiors of voids toward the denser regions that form clusters and superclusters. To identify voids more precisely, astronomers use different methods depending on the kind of data they have. One common technique is to treat the distribution of galaxies as a landscape: peaks where clusters are dense, valleys where they are sparse. Algorithms then trace the contours of these valleys, grouping together areas of low density into three-dimensional shapes. Another method involves smoothing out the galaxy map, looking for extended regions where the density consistently stays below a chosen threshold. These computational approaches are crucial because voids aren't obvious just by looking at the night sky. To the human eye, even the emptiest parts of the universe appear filled with countless stars. Only through statistical mapping does their true hollowness emerge. As our observations have improved, astronomers have learned that voids come in a remarkable range of sizes. The smallest might span just a few million light-years, like pockets of thin air between filaments. The largest stretch across hundreds of millions of light-years, rivaling the great walls and clusters that define the web itself. Interestingly, voids also seem to evolve over time. Early in the universe's history, when matter was more evenly spread, the contrast between dense and empty regions was subtle. Over billions of years, the voids expanded, their boundaries sharpened, and their interiors thinned out further. This process continues even now. In simulations, we can see voids slowly merging, absorbing one another, and stretching as the universe itself expands. Their dynamics reveal an important aspect of cosmic physics. In dense regions, gravity dominates, slowing the expansion of space locally. In voids, however, the opposite occurs. With so little matter to slow it down, space expands faster. These regions act almost like engines of cosmic acceleration, pushing the surrounding matter outward. Some cosmologists even suggest that the collective expansion of voids contributes to the overall rate at which the universe is stretching. This idea is still debated, but it highlights how voids are not merely gaps. They're active components in the universe's growth. To study them in detail, astronomers rely on both observation and simulation. Large-scale surveys have mapped thousands of voids across the sky, revealing their shapes and relationships to nearby structures. Meanwhile, cosmological simulations allow scientists to model how voids form and evolve under different assumptions about dark matter, dark energy, and the laws of gravity. By comparing these simulations to the observed universe, researchers can test which theories best match reality. For example, if voids grow faster than expected, it might suggest that dark energy is stronger than our current models predict. One of the subtle challenges in defining a void is deciding where it ends. Unlike a planet or a star, a void doesn't have a clear boundary. Its edges blend gradually into the surrounding filaments, like mist dissolving into air. Astronomers must choose a threshold density, a value below which the region counts as empty enough. This choice can vary from one study to another, depending on the focus. Some researchers define voids conservatively, including only the deepest regions. Others use broader definitions to capture the entire underdense area, including the outer layers where galaxies begin to appear again. Despite these differences, a consistent picture has emerged. The universe is dominated not by matter, but by emptiness. When we calculate how much of the cosmos lies within voids, the answer is astonishing. Roughly 80% of the observable universe's volume is made up of these underdense regions. Yet most of the mass resides in the remaining 20%, concentrated in filaments and clusters. It's a striking imbalance that reveals the true nature of cosmic structure. The universe is vast not because it's filled with things, but because it's mostly not. Even so, voids are not places of absolute quiet. Within them, the faint whisper of cosmic history still lingers. Radiation from distant galaxies passes through them unimpeded, allowing astronomers to use these regions as transparent windows into the universe's past. The light that travels across a void encounters less gravitational distortion, giving scientists cleaner measurements of cosmic expansion. For this reason, voids are becoming powerful tools in modern cosmology. By studying how light behaves as it passes through emptiness, we can learn about the shape, size, and fate of the universe itself. We are used to focusing on what is there, the stars, the galaxies, the clusters. But in the grand pattern of the cosmos, what defines everything else is what lies between. Emptiness, when measured carefully, turns out to be one of the most informative quantities in all of astronomy. Dark matter, the unseen framework. For decades, astronomers suspected that something hidden was influencing the cosmos. The first clues came in the 1930s, when Swiss astronomer Fritz Zwicky studied a cluster of galaxies in the Coma constellation. He found that the galaxies were moving far too fast to be held together by the gravity of their visible stars alone. Something unseen was providing the extra pull needed to keep the cluster intact. Zwicky called it dunkle materie, dark matter, though at the time few took the idea seriously. In the 1970s, astronomer Vera Rubin and her collaborator Kent Ford studied how stars moved within spiral galaxies. According to Newton's laws, stars farther from the galactic center should orbit more slowly, just as planets further from the Sun move more sluggishly around their star. But Rubin found that stars in the outer regions of galaxies were moving just as fast as those near the center, sometimes even faster. The only explanation was that galaxies contained much more mass than what was visible in stars and gas. An invisible halo of matter, extending far beyond the bright disk, had to be there, anchoring the galaxy with its gravity. These suggested that what we are merely the surface decorations of something far larger and darker. Over time, observations of galaxy clusters, gravitational lensing, and the CMB all confirm the same picture. Dark matter outweighs normal matter by about 5 to 1. To understand what dark matter actually does, scientists turned to simulations. By recreating the universe inside computers, they could watch how invisible matter interacts under the laws of gravity. Starting from the tiny density fluctuations seen in the early universe, dark matter began to clump together under its own gravity. Because it doesn't interact with light or heat, it could collapse more efficiently than normal matter, forming a vast network of filaments, sheets, and nodes. In these simulations, galaxies form like droplets along the dark matter filaments. As gas cools and flows along the invisible threads, it collects in the densest regions, the intersections of dark matter filaments, where it can form stars and galaxies. The galaxies light up these intersections, tracing out the underlying dark framework. What we see through telescopes is only the luminous frosting on top of an invisible cake. One of the most famous of these simulations, the Millennium simulation, modeled the evolution of more than 10 billion dark matter particles over a volume spanning 2 billion light-years. When the simulation ran forward in time, it produced a structure almost indistinguishable from the real universe. The match was too precise to be coincidence. Without dark matter, galaxies would not have had enough gravitational glue to form or survive. Because dark matter interacts only through gravity, it doesn't clump into small, dense bodies like ordinary matter does. Instead, it forms smooth, extended halos around galaxies and clusters. These halos overlap and merge over time, creating the filaments that connect different regions of the universe. In the densest intersections, the halos become massive enough to trap enormous amounts of gas, triggering the birth of galaxies. Everywhere else, where the dark matter density is lower, the space remains mostly empty, forming the great cosmic voids. We can't see dark matter directly, but we can observe its effects with extraordinary precision. One of the clearest signs comes from gravitational lensing. By measuring these distortions, astronomers can create mass maps showing structures that line up perfectly with the predictions from dark matter simulations. Perhaps the most dramatic example of this came from the Bullet cluster, a system formed by the collision of two galaxy clusters about 3.8 billion light-years away. When astronomers observed it with both optical and X-ray telescopes, they saw that the hot gas, which makes up most of the normal matter, had slowed down and piled up in the center from the impact. But the majority of the mass, revealed by gravitational lensing, had passed straight through and now lay ahead of the visible gas. This meant the bulk of the cluster's matter was dark matter, behaving exactly as expected for a substance that doesn't interact with normal matter except through gravity. Without it, the early universe would have remained too smooth for galaxies to form. The slight ripples in density visible in the CMB were far too small for ordinary matter to clump together on its own. But dark matter, unaffected by radiation pressure, began collapsing into small halos long before normal matter could. Despite all this evidence, scientists still don't know what dark matter is made of. It could be composed of unknown particles that rarely interact with normal matter, perhaps something like the hypothetical WIMPs, weakly interacting massive particles, or axions, tiny particles that could pervade space. Experiments are still searching for these elusive building blocks, hoping to catch even the faintest signal. Every time we look at the rotation of a galaxy, the bending of light around a cluster, or the patterns in the CMB, we are seeing dark matter's handiwork. If all the dark matter in the universe were suddenly removed, the galaxies would fly apart, the clusters would dissolve, and the grand cosmic web would unravel. The night sky itself would lose its structure, leaving only scattered remnants adrift in an expanding void. As telescopes like the James Webb Space Telescope and the Vera C. Rubin Observatory peer deeper into space and time, they are seeing galaxies forming along the same filaments that dark matter simulations predicted decades ago. Observations of the faintest, most distant galaxies show them clustering where dark matter halos are thought to be densest, as if the invisible architecture was already in place, waiting for light to fill it. In some regions, astronomers can even infer the shape of dark matter directly by studying the motion of galaxies. In a massive cluster, galaxies move as if embedded in a giant invisible halo. The speed of their motion tells us the mass of that halo, revealing the hidden contours of the dark matter structure. These measurements confirm again and again that galaxies are glowing beads strung along invisible filaments of dark matter. There is a quiet irony in all this. The substance that gives the universe its shape is something we have never seen and cannot touch. Yet the very structure of the universe follows its design. The 1981 discovery that shocked cosmology. In 1981, at Kitt Peak National Observatory in Arizona, astronomer Robert Kirshner and his colleagues August Oehmler, Paul Schechter, and Stephen Schechtman were studying the large-scale distribution of galaxies. Their goal was to measure redshifts to better understand how galaxies were grouped in space. The team worked with photographic plates and spectrographs that captured only a few galaxies at a time. But even with these limited tools, they started to notice something strange. When they plotted their data, the redshifts of hundreds of galaxies in the direction of the constellation Boötes, a pattern appeared. Instead of the expected spread of galaxies filling space, there was a sudden enormous gap, a region roughly 250 million light-years across that seemed to contain almost nothing. At first, the astronomers assumed there had to be an error. Maybe the survey's field of view was too small, or perhaps the galaxies in that region were too faint to detect. But as more data came in, the hole refused to disappear. Every new observation only confirmed the same strange reality: a vast region of space almost completely empty of galaxies. The team called it, somewhat casually at first, the Boötes void. It was a name that understated just how shocking the find really was. When Kirshner's team published their results, the reaction from the astronomical community was immediate and mixed. Some were skeptical, suggesting that the void might be an artifact, a coincidence of limited data, or a gap in the survey. Others were fascinated but confused, because no model of cosmic structure at the time predicted such a thing could exist. The universe, according to the prevailing theories, should have been relatively uniform at large scales. Galaxies might cluster together, yes, but not in a way that would leave a hole hundreds of millions of light-years wide. To visualize the scale of the Boötes void is almost impossible. It's one of the largest known voids in the observable universe, about 700 million light-years from Earth and nearly 330 million light-years across. Some astronomers questioned whether selection effects, biases in how galaxies were chosen for observation, might have created an artificial gap. Kirshner and his team responded by expanding their survey, gathering data from additional telescopes and cross-checking with other catalogues. Each new layer of evidence confirmed the same conclusion: the void was real. Over the next few years, as other redshift surveys began to probe deeper into the sky, similar though smaller voids were found elsewhere. But the Boötes void remained special, both because of its sheer size and because it was the first clear proof that the universe's large-scale structure wasn't just random. When the discovery was first presented at conferences, it was met with the kind of skepticism that only paradigm-shifting ideas attract. Some cosmologists compared it to the early discoveries of planetary motion or cosmic expansion, results so counterintuitive that they demanded the rewriting of existing frameworks. The timing of the discovery was crucial. Just a few years later, computer simulations of cosmic structure would begin to show how dark matter could produce precisely such patterns. The Boötes void, it turned out, wasn't an anomaly at all. But in 1981, before dark matter was well understood and before the cosmic web was confirmed, the void looked like a cosmic mistake. The surprise of the Boötes void wasn't just its emptiness, it was its coherence. Galaxies on its edges seemed to form a loose boundary. That image resonated with later descriptions of the universe as cosmic foam, where galaxies outline the walls of enormous bubbles and the voids are their interiors. But at the time, this analogy hadn't yet taken root. For Kirshner's team, the void was simply an observation they couldn't ignore. For months after the initial paper, debates filled journals and conferences. Some speculated that the void might have been inflated by local variations in the early universe's density field. Others wondered if it might be connected to dark energy or exotic forms of matter that repelled gravity instead of attracting it. Kirshner himself described the discovery as both thrilling and unsettling. In interviews, he spoke about how it felt to find something that forced him to reconsider everything he thought he knew about the cosmos. In science, such moments are rare. Most discoveries fill gaps in existing theories. A few, like the Boötes void, create gaps that theories must stretch to cover. As the years went on, the Boötes void became a symbol of the unknown. Looking back, it's clear that 1981 marked a turning point in how we perceive the cosmos. The discovery of the Boötes void didn't just fill a blank spot in the sky, it showed that emptiness itself could be an organizing principle. The cosmic foam model. The foam-like nature of the cosmos provided a new way to think about how gravity sculpts matter across space. In a foam, pressure differences between adjacent bubbles cause their walls to shift, merge, and reorganize over time. In the cosmic foam, it is gravity that drives these changes. Dense filaments grow denser as matter streams along them, while voids expand as they lose material to their boundaries. The result is a self-organizing structure that, though complex in detail, follows simple underlying principles. The universe, left to evolve under the pull of gravity and the push of expansion, naturally develops this bubbly topology. In the 1980s, the work of cosmologists like Jan Einasto, Alexei Starobinsky and their collaborators helped formalize this picture. Their galaxy surveys revealed a cellular universe, a foam-like pattern where dense superclusters formed the walls and filaments around enormous underdense cells. Later observations confirmed this pattern again and again. Modern surveys allowed scientists to visualize this cosmic structure in unprecedented detail. When rendered in 3 dimensions, the galaxy distribution looks strikingly like the froth on the surface of an ocean, frozen in time and stretched across billions of light-years. The analogy to foam is deeply mathematical. In both foams and cosmic structure, geometry and topology play crucial roles. The boundaries of voids meet at filaments, which themselves intersect at dense nodes, much like the edges and vertices of bubbles in a cluster. Mathematically, this arrangement can be described using concepts from topology and graph theory, where the connections between nodes and edges form a cosmic network. These mathematical frameworks allow scientists to quantify how interconnected the universe's structure is, how large the average voids are, and how galaxies cluster within the filaments. The equations describing foams, like those derived from the work of physicist Joseph Plateau in the 19th century, turn out to echo the relationships found in cosmic structure. In both cases, nature seems to favor efficient packing and minimal surface energy, even though in the universe's case, gravity replaces surface tension as the guiding force. The cosmic foam appears to repeat itself on many scales. While galaxies and clusters occupy smaller walls and filaments, larger regions of the web display the same pattern, hinting at a kind of fractal-like hierarchy. The deeper astronomers peer into the universe, the more they find this structure repeating. Dense regions connected by thin bridges surrounding great cavities. This self-similarity gives the universe an organic quality, as though the same rules that govern a soap bubble or a cell membrane also govern the arrangement of galaxies on scales of hundreds of millions of light-years. It suggests that structure in the cosmos arises from fundamental processes that are scale-independent, gravity and expansion interacting across all distances in similar ways. Within this cosmic foam, matter flows like an invisible current. Over billions of years, these flows reinforce the walls of the foam, while the interiors of voids become increasingly empty. Computer simulations vividly show this dynamic behavior, vast, underdense bubbles slowly swelling and merging, while the filaments between them tighten and thicken. It's a living structure, an evolving network that shifts shape as the universe expands. On cosmic timescales, the foam changes subtly, its bubbles stretching as dark energy accelerates the expansion, and its filaments gradually thinning as matter drains into the densest centers. Observationally, the cosmic foam model has given astronomers a new framework for interpreting galaxy surveys. When telescopes map millions of galaxies, what emerges is not a random scatter, but an organized, three-dimensional network. By analyzing this distribution statistically, scientists can extract key cosmological parameters, such as the average density of matter, the amplitude of primordial fluctuations, and the influence of dark energy. The foam's pattern becomes a kind of cosmic fingerprint, reflecting the conditions of the early universe. The size and shape of voids, for example, can tell us how quickly the universe has expanded since the Big Bang. The thickness of filaments hints at the properties of dark matter, while the clustering of galaxies on the foam's walls reveals how gravity has acted over cosmic time. At small scales, within galaxies or clusters, everything seems turbulent and unpredictable, governed by the messy dynamics of star formation and galactic collisions. But when viewed from far enough away, a hidden symmetry appears. The universe organizes itself into an intricate but coherent pattern. This duality gives the cosmic foam a sense of balance, as though chaos on small scales naturally gives rise to structure on large ones. Modern visualizations of the cosmic web, generated from simulations involving billions of particles, bring this foam-like universe vividly to life. Such models help researchers study not just where galaxies are, but why they are there. In recent years, astronomers have begun to measure the foam's structure more precisely using new tools. These studies confirm what galaxy surveys had long suggested, that the same bubble-like topology extends into the dark matter realm as well. The unseen scaffolding of the universe follows the same geometry. Just as a cluster of soap bubbles can illustrate the balance of forces in a fragile system, the universe's bubble-like web reveals how gravity and expansion coexist in a delicate equilibrium. The bubbles of the cosmos are not filled with air but with space, expanding, merging, reshaping the very texture of reality. Galaxies in the desert, the few that exist inside. Inside the vast expanse of the Boötes void, there are galaxies, but only a few. Scattered like islands in an endless sea of darkness, they drift alone, separated from each other by tens or even hundreds of millions of light years. The emptiness surrounding them is so extreme that even the nearest neighbors would be invisible to the naked eye, their light swallowed by distance and time. Yet despite the desolation, these galaxies exist. Their presence in such an unlikely place has become one of the most intriguing puzzles in modern cosmology. When Robert Kirshner and his team first charted the Boötes void, they found almost nothing at all. Out of the thousands of galaxies expected in such a volume, only a handful showed up on their redshift maps. For years, astronomers wondered if the void might truly be empty, but as instruments improved, faint signals began to emerge. Careful surveys revealed small smudges of light that corresponded to real galaxies hiding in the darkness. Eventually, astronomers identified roughly 60 of them within the void, a tiny number compared to what should exist, but enough to prove that even the loneliest regions of the cosmos are not completely barren. These galaxies are strange survivors. Many appear smaller and dimmer than average. Their faintness is partly due to their isolation. With few nearby galaxies to interact or merge with, they evolve differently. In dense environments like galaxy clusters, collisions and mergers are common, driving bursts of star formation and shaping galaxies over billions of years. But inside the Boötes void, such encounters are almost non-existent. Each galaxy lives largely untouched, its evolution determined by internal processes rather than external influence. By studying these void galaxies, scientists can observe how galaxies behave without the gravitational tug and pressure of their crowded counterparts. It's a kind of natural experiment. What happens when a galaxy is left alone for billions of years? The results are fascinating. Many void galaxies show signs of ongoing star formation, even though their gas reserves should have been depleted long ago. Some contain unusually large amounts of neutral hydrogen, the raw material for new stars, suggesting that they've been able to retain their gas instead of losing it to gravitational interactions. Others appear to have delayed evolutionary timelines. In galaxy clusters, the dense environment often strips galaxies of gas and halts star formation early. But in the void, galaxies evolve at their own pace, forming stars slowly over billions of years. This makes them appear younger, with bluer colors and more active star-forming regions. In a sense, they are cosmic time capsules, snapshots of how galaxies might have looked in the early universe. One of the most studied examples is a galaxy known as Boötes Void Galaxy number 1, one of the first confirmed inhabitants within the void. Observations suggest it's a faint spiral galaxy, its delicate arms stretched thin in the darkness. Unlike the massive, crowded spirals found in denser regions, it shows no evidence of past collisions or distortions. Its stars move in quiet orbits, largely undisturbed for billions of years. There are others like it, small, faint galaxies, barely visible even in long exposures. But each one carries clues about how galaxies can form and survive in isolation. The mere existence of these galaxies raises deep questions. How did they form in such an empty region in the first place? In standard cosmological models, galaxies form in regions where dark matter is densest. Voids, by definition, are regions with very low dark matter density. Yet somehow, small fluctuations in that density, tiny ripples left over from the early universe, were still enough to seed galaxy formation in a few scattered pockets. These galaxies may represent the rare peaks in an otherwise flat landscape of gravitational potential, the last remnants of structure that barely crossed the threshold for star formation. Their motion also provides important insights. Astronomers have measured the velocities of some of these galaxies and found that many are drifting toward the edges of the void, pulled slowly by the gravity of the denser regions beyond. It's as if the galaxies are caught in a slow cosmic tide, born in the middle of the desert, and gradually drawn outward over billions of years. This movement helps confirm models that describe voids as expanding under the influence of cosmic expansion and dark energy. The low-density regions effectively grow larger as matter flows out of them, leaving behind even emptier interiors. Some astronomers speculate that the galaxies now within the Boötes void may not have formed there at all. Instead, they could have drifted in from surrounding filaments, carried by gravitational flows. In this scenario, the void acts like a gentle funnel, slowly gathering stray galaxies over cosmic time. If true, this could explain why the few galaxies inside the void often lie closer to its edges than its center. They might be newcomers, cosmic wanderers that have strayed too far from the galactic highways of the universe. Others propose a different story, that these galaxies are the survivors of ancient structures that once existed before the void expanded. In the early universe, before the large-scale cosmic web took its current shape, regions of slightly lower density still contained enough matter to form small galaxies. As the universe expanded, these regions became more and more empty, stretching apart until only a few galaxies remained, stranded in isolation. If so, the Boötes void could be a fossil record of how the first structures in the universe evolved, a place where the earliest galaxies endured, while everything around them thinned into nothing. Studying these galaxies isn't easy. Their faintness makes them difficult to observe, and their great distances mean that even powerful telescopes, like the Hubble Space Telescope, can capture only limited detail. Newer instruments, such as the James Webb Space Telescope and large ground-based observatories, like the Vera C. Rubin Observatory, promise to change that. With their sensitivity, astronomers hope to map the properties of these void galaxies in unprecedented detail: their star populations, gas content, and chemical composition. Each data point helps refine our understanding of how galaxies can form and persist in the most unlikely environments. One intriguing aspect of these galaxies is their apparent resilience. Despite being isolated from the cosmic web's main arteries of gas and dark matter, many show signs of long-term stability. They haven't collapsed or burned out. Instead, they've quietly continued forming stars, maintaining their structure in near-perfect solitude. This stability suggests that the internal dynamics of galaxies, the balance between gravity, gas pressure, and dark matter, can sustain them even when cut off from external influences. In this way, the galaxies of the Boötes void show that galaxies don't necessarily need to be part of crowded clusters or filaments to survive. The universe provides many paths to persistence, and isolation, in some cases, can be a form of protection. Without nearby gravitational interactions, these galaxies avoid the violent collisions that can tear others apart. Their slow, steady evolution paints a quieter picture of cosmic life. For cosmologists, these lonely galaxies are essential data points. Every faint dot within the void tells a story about balance, endurance, and the quiet tenacity of matter in a universe dominated by emptiness. Perhaps the most poetic aspect of all is that we can see them at all. Light from these isolated galaxies has traveled hundreds of millions of years to reach us, crossing the immense gulf of the void. During that journey, it passed through regions of nearly perfect darkness, where not a single star shone. The photons that now strike our telescopes are survivors of that journey, carrying with them the silent testimony of galaxies that have existed for billions of years, far from everything else. Proving the Boötes void wasn't an accident of observation, Early redshift surveys were often pencil beam studies, long, thin slices of the sky, covering a narrow cone-shaped region. Such a limited field of view could easily produce gaps or distortions in the apparent distribution of galaxies. What looked like a vast empty sphere might, in reality, be just a poorly sampled region or a statistical gap created by the survey's shape. Kirshner's team was aware of these issues and spent months double-checking their data. They re-examined the redshifts, verified the positions, and compared their results with other sky surveys. When they plotted galaxy positions in 3 dimensions, the result was unmistakable: a gaping, spherical region in the constellation Boötes that contained almost no galaxies. Still, skepticism ran deep. Astronomers are trained to distrust anomalies until they've been tested from every angle. Over the next few years, other teams began to look into the same region using independent observations. Radio telescopes searched for neutral hydrogen emissions, a telltale sign of galaxies that might be too faint optically. Optical telescopes probed deeper, looking for faint smudges that might have been missed. The result was the same. As surveys improved, so did confidence in the void's reality. The CFA Redshift survey provided further evidence in the mid-1980s. It showed not just the Boötes void, but other, smaller voids scattered throughout the cosmos. This discovery marked a turning point. What had first seemed like an observational anomaly became a crucial clue to the universe's large-scale organization. But the process of verification wasn't simple. Astronomers had to be certain that what they were seeing wasn't due to dust, light absorption, or instrument bias. They ruled out interstellar extinction, the dimming of distant galaxies by dust in the Milky Way, since the Boötes region lies well above the galactic plane, where such effects are minimal. They also checked for the possibility of light contamination or calibration errors in the spectrographs, but none of these could account for a void hundreds of millions of light-years wide. As digital detectors replaced photographic plates, astronomers gained even sharper tools to test the Boötes void. Charge-coupled devices, or CCDs, far more sensitive than film, allowed surveys to reach fainter magnitudes and detect galaxies that would once have been invisible. Yet even with this new technology, the vast gap remained. The verification process itself was a milestone in observational cosmology. It showed how science advances not by assuming extraordinary discoveries are true, but by attempting to disprove them. Only after every possible source of error had been eliminated did the Boötes void graduate to a confirmed cosmic structure. Over time, the methods for detecting and verifying voids became more sophisticated. Modern surveys have mapped millions of galaxies. In these vast datasets, the Boötes void stood out exactly where Kirshner's team had found it. Independent teams using different instruments, wavelengths, and selection methods all confirmed its presence. Even today, the process of verifying voids continues to evolve. Scientists now use not only light, but also gravitational effects to confirm their existence. The Boötes void itself has been studied through these methods, confirming that its mass density is indeed lower than surrounding regions. Some of the earliest doubts now seem almost quaint. In the 1980s, one astronomer reportedly joked that the Boötes void was simply where they forgot to look. But decades of observations have shown that this was not the case. In a way, the story of the Boötes void's verification mirrors the scientific process itself, a constant balancing act between skepticism and wonder. Each new piece of evidence forced scientists to reconsider what was possible. Each test that failed to explain away the void only deepened its mystery. And in the end, what remained was a real and measurable absence. Cosmic distance ladders and the scale of emptiness. Measuring sizes and distances in the universe is not like measuring the size of a continent. There is no cosmic ruler that can be stretched across billions of light years, no tape measure that can reach from one galaxy to another. Instead, astronomers rely on a sequence of overlapping techniques, each one reaching a little further than the last. These techniques form what is known as the cosmic distance ladder. a carefully built chain that allows humanity to gauge the true scale of the cosmos. It is through this ladder that we begin to understand just how large the empty regions between galaxies truly are. At its most fundamental level, the cosmic distance ladder begins with geometry. The first rung is parallax, a simple but powerful method based on the apparent shift in position of a nearby star as Earth moves around the Sun. As our planet traces its orbit, close stars appear to move slightly against the more distant background, just as your thumb seems to jump from side to side when you look at it with one eye and then the other. By measuring that tiny angular shift, astronomers can calculate the star's distance using basic trigonometry. For centuries, this was the most direct and reliable way to measure distances in space. The first successful stellar parallax was measured in 1838 by Friedrich Bessel for the star 61 Cygni. Its shift was only a fraction of a second of arc, an almost imperceptible wobble, but it was enough to show that the stars are unimaginably far away. Modern space telescopes like Hipparcos and Gaia have pushed this technique to extraordinary precision, measuring parallaxes for over 1 billion stars. These measurements define the first solid rungs of the ladder, anchoring all other distance methods to a firm geometric base. But parallax alone cannot take us far enough. It works only for relatively nearby stars within our own galaxy. To reach beyond, astronomers turn to the next rung, standard candles. These are objects whose intrinsic brightness, their true luminosity, is known. By comparing how bright they appear from Earth to how bright they should be, scientists can calculate their distance. One of the most important standard candles in astronomy is the Cepheid variable star. Cepheids pulse rhythmically, their brightness rising and falling in a predictable pattern. In the early 20th century, astronomer Henrietta Swan Leavitt discovered that the longer the period of a Cepheid's pulsation, the brighter it truly is. This relationship, known as the Leavitt law, became one of the cornerstones of cosmic measurement. By observing a Cepheid's period and apparent brightness, astronomers could determine its distance, and by extension, the distance to the galaxy that contained it. This method extended humanity's reach far beyond the Milky Way. In the 1920s, Edwin Hubble used Cepheid variables to measure the distance to the Andromeda Nebula and proved it was not a nearby gas cloud, but an entire galaxy, millions of light years away. It was the first clear evidence that our universe is vast and filled with galaxies scattered across unimaginable distances. Yet even Cepheids have their limits. They can only be seen in relatively nearby galaxies. To measure distances on truly intergalactic scales, astronomers needed even brighter standard candles, cosmic beacons visible across billions of light years. This role is filled by type Ia supernovae. A type Ia supernova occurs when a white dwarf star in a binary system accumulates too much material from its companion and undergoes a catastrophic thermonuclear explosion. These explosions are incredibly luminous, briefly outshining entire galaxies. More importantly, they all reach nearly the same peak brightness because they ignite at a consistent mass, the Chandrasekhar limit. This uniformity makes them excellent distance indicators. By measuring how bright a supernova appears from Earth, astronomers can infer how far away it is with remarkable accuracy. Using type Ia supernovae, scientists have measured distances out to billions of light years, mapping the large-scale structure of the universe itself. These measurements revealed not only the arrangement of galaxies and voids, but also the astonishing fact that the expansion of the universe is accelerating, a discovery that led to the concept of dark energy. Together, parallax, Cepheids, and supernovae form the backbone of the cosmic distance ladder. Each rung overlaps with the next, ensuring that measurements remain consistent. Parallax anchors Cepheids. Cepheids calibrate supernovae, and supernovae, in turn, define the scale of cosmic expansion. The accuracy of the entire ladder depends on how well each step is measured and linked. Over time, refinements in technology and observation have tightened these links, turning rough estimates into precise measurements. The ladder doesn't stop there. On even larger scales, astronomers rely on redshift to estimate distances. The farther away a galaxy is, the faster it recedes, and the more its light is shifted toward the red end of the spectrum. This relationship, known as Hubble's law, provides a way to convert redshift into distance. But redshift is not an absolute measure on its own. It must be calibrated using the lower rungs of the ladder. Without parallax and standard candles to set the scale, redshift distances would be mere guesses. By combining these methods, astronomers have been able to chart the positions of millions of galaxies and the enormous voids between them. To make these measurements more reliable, modern astronomers use a combination of techniques rather than relying on a single one. For instance, they use Cepheid variables to determine the distance to galaxies that have also hosted type Ia supernovae, cross-checking the two methods. In other cases, they calibrate redshift distances using galaxies with known supernova distances, linking the near and far universe seamlessly. This interlocking system ensures that no single error can throw the entire cosmic scale off balance. The development of space-based observatories has been crucial in improving the ladder's accuracy. The Hubble Space Telescope, for example, has observed Cepheid variables in distant galaxies with unprecedented clarity, free from the distortions of Earth's atmosphere. Its observations helped refine the value of the Hubble constant, the rate at which the universe expands, which in turn affects distance calculations for the entire cosmos. The more precisely we know that constant, the better we can estimate the scale of voids and structures across the universe. Even with these advances, the cosmic distance ladder is still being refined. One of the most fascinating aspects of modern cosmology is the slight tension between different measurements of the Hubble constant. When derived from local Cepheid and supernova distances, it gives one value. When inferred from the CMB, it gives another. This discrepancy, known as the Hubble tension, has prompted scientists to re-examine the ladder from top to bottom, checking for hidden biases, unaccounted physics, or perhaps signs of new cosmic phenomena. But despite these uncertainties, the ladder remains one of the most remarkable achievements in human history. It allows us to measure the immeasurable, to assign numbers to the voids between galaxies, and quantify the depths of cosmic nothingness. Without it, the universe would remain a flat picture, a projection of light without depth or scale. Each rung of the ladder represents both a technological leap and a conceptual one. Through it, we can now describe the universe in numbers that once would have been inconceivable. We can say that the nearest large galaxy, Andromeda, is 2.5 million light-years away. We can measure that the Virgo cluster, one of the nearest galaxy clusters, lies about 54 million light-years distant. And we can estimate that the Boötes void stretches for hundreds of millions of light-years across. The cosmic distance ladder transforms the night sky from a flat backdrop into a living landscape with depth, scale, and perspective. It reveals that the spaces between galaxies are not small gaps, but immense oceans of emptiness, each one larger than imagination can easily contain. Baryon acoustic oscillations, the universe's ancient imprint. Long before the first galaxies formed, the universe was a dense, hot sea of light and matter mixed together. It was a time when photons were constantly colliding with electrons and protons, keeping everything bound into a tightly coupled plasma. This early universe wasn't still or silent, it vibrated. Across its vastness, waves of pressure rippled outward, sound waves, born from the tiny quantum fluctuations that existed moments after the Big Bang. These waves pulsed through the young cosmos, compressing and stretching the plasma much like ripples moving through water. Today, the frozen echoes of those primordial sound waves remain imprinted on the universe, written into the distribution of galaxies and the pattern of cosmic voids. They are known as Baryon acoustic oscillations, or BAOs for short. To imagine what the early universe sounded like, it helps to picture an immense glowing fog filled with pressure and motion. The term baryon refers to normal matter, the protons and neutrons that would eventually form atoms, while acoustic oscillations describes how these particles moved in rhythmic patterns, driven by the competition between gravity and radiation. Where matter began to clump together under gravity, the intense radiation trapped within the plasma pushed outward, creating expanding shells of compression. Every dense spot became the center of a spherical sound wave, racing outward at nearly half the speed of light. These waves overlapped and interfered with one another, creating a complex network of peaks and troughs, regions slightly denser or thinner than average. For nearly 380,000 years after the Big Bang, this cosmic symphony continued. But then came a dramatic shift. The universe cooled enough for protons and electrons to combine into neutral hydrogen atoms, allowing light to travel freely for the first time. This moment, known as recombination, effectively ended the sound waves. The radiation that had been pushing the plasma apart was released as the CMB. Meanwhile, the matter that had been part of those oscillations was left with subtle imprints, slightly denser shells surrounding the original high-density regions. These shells became the seeds of structure, the places where galaxies and clusters would later form, separated by the great voids we see today. The scale of these ancient sound waves is astonishing. Each one traveled about 500 million light-years before being frozen in place by the cooling of the universe. That distance became another kind of cosmic standard ruler, a natural scale built into the very fabric of space. Over billions of years, gravity amplified the densest regions while the less dense areas evolved into voids. But even after all that time, the imprint of those primordial ripples remains visible. If you measure the distances between galaxies on average, you find that they are slightly more likely to be separated by about 500 million light-years than by other distances. That regularity, like a faint ancient rhythm hidden in the arrangement of galaxies, is the signature of Baryon acoustic oscillations. It took modern instruments and massive surveys to uncover this hidden rhythm. In the early 2000s, when scientists analyzed the data from the SDSS, they noticed a faint bump in the statistical distribution of galaxy separations. It was only a tiny deviation from randomness, but it was exactly what theory predicted from Boötes. This bump confirmed that the large-scale pattern of galaxies still carries the fingerprint of sound waves that rippled through the universe when it was less than 400,000 years old. For cosmologists, it was like finding an ancient fossil embedded in the universe. Boötes act as a ruler for measuring cosmic expansion. Because the scale of the original sound waves is known, astronomers can compare it to how large it appears in the sky today. If the universe has expanded more, the apparent size of that ruler will look smaller. By tracking this effect at different distances, different epochs in time, scientists can reconstruct how fast the universe has been expanding throughout its history. This makes Boötes one of the most reliable tools for studying dark energy. Beyond their role in measuring expansion, Boötes also explain why the universe looks the way it does, the grand architecture of filaments, walls and voids that make up the cosmic web. The peaks and troughs of those early sound waves corresponded to regions of slightly higher or lower density in the young plasma. Over billions of years, gravity amplified these differences, creating a scaffolding that determined where matter would collect and where it would empty out. The densest peaks became clusters of galaxies. The troughs became voids. Even the largest structures known, like the Sloan Great Wall or the Hercules Corona Borealis Great Wall, trace their origins back to the distribution shaped by these ancient ripples. Visualizing this process in modern simulations is mesmerizing. When cosmologists recreate the evolution of the universe using computers, they begin with a smooth distribution of matter, marked by the faint pattern of Boötes. Watching the universe grow in these simulations is like seeing frozen sound waves slowly transformed into a living cosmic structure, a record of vibration turned into architecture. In this sense, Boötes serve as the universe's own memory. They preserve information about its infancy, locked into the cosmic web like grooves on an ancient record. Every filament, every cluster, every void is part of that record, a direct consequence of those early vibrations. Even enormous structures like the Boötes void can be traced, in a way, to the same underlying physics. They are the negative spaces left behind by those rippling sound waves, the regions that expanded outward as matter flowed toward the compressions. The voids are the quiet echoes of those ancient tones, stretched across billions of light years. Imagine freezing a sound wave in mid-air, a ripple of pressure locked forever in space. That's what happened to the universe on a cosmic scale. The pressure waves stopped moving when the universe became transparent, but their shape remained imprinted in the matter that filled space. Even today, researchers are refining their measurements of BAOs with incredible precision. Surveys like Euclid are mapping the cosmic web in greater detail than ever before. By comparing these maps with models of the early universe, scientists can trace how those primordial oscillations evolved into the structures we observe. The more accurately we measure the ripples, the better we understand not only how the universe grew, but also how it continues to stretch under the influence of dark energy. There are no true sounds in the modern universe's vacuum, but in its early plasma, the entire cosmos hummed. It was a universe that rang with pressure waves, a deep resonant music that shaped everything to come. Those vibrations did not fade completely. Their faint echo lives on, carved into the cosmic web, in the distances between galaxies and the emptiness of the voids. Every map of the universe we draw today is a continuation of that ancient rhythm. Simulating nothing, computational models of voids. Inside the laboratories of cosmologists, entire universes are born, not through telescopes or rockets, but inside supercomputers. In a windowless room filled with humming machines, the cosmos is recreated as code. Each particle, each photon, each ripple of dark matter is rendered in digital form, obeying the same physical laws that govern reality. These simulations are predictive experiments, tools that allow scientists to rewind and replay the history of everything, from the first moments after the Big Bang to the silent, empty voids that now span billions of light years. To simulate a universe, you must begin with its ingredients. The recipe starts with a uniform soup of matter and energy, an early universe still hot and smooth, nearly featureless, except for the tiniest fluctuations in density. In the simulation, billions of digital particles are spread across a three-dimensional grid, each one representing a lump of dark matter or baryonic matter. Then, as the program begins to run, gravity takes over. The particles attract one another, forming filaments and knots. The first thing that emerges in these models is the cosmic web. Galaxies cluster along thin threads of matter, while between them, enormous regions remain mostly empty. Early simulations in the 1980s and 1990s could already reproduce this foam-like pattern, even though they worked with crude approximations and limited computing power. As technology improved, simulations became vast and precise. They no longer tracked a few thousand particles, but billions, each governed by Newtonian and relativistic laws, with parameters for dark energy, cosmic expansion, and even feedback from exploding stars. The previously mentioned Millennium simulation, conducted in 2005 by the Max Planck Institute for Astrophysics, tracked 10 billion particles of dark matter inside a cubic region more than 2 billion light-years wide. When visualized, it looked eerily familiar. A lattice of luminous filaments surrounding deep, dark cavities. These voids matched the shapes and scales astronomers had observed through redshift surveys. In the years since, even larger and more detailed simulations have been developed. The Illustries, Eagle, and most recently, the Illustries TNG project. These models include not just dark matter, but also gas physics, radiation, star formation, and feedback processes. They show how galaxies form and die, how their winds sculpt the surrounding medium, and how those forces subtly affect the edges of voids. When these simulations are allowed to evolve for billions of digital years, they produce a cosmic landscape that looks uncannily like reality. The resemblance is so striking that astronomers now use these simulations as laboratories to test new ideas before searching the sky for evidence. Because voids are dominated by dark energy and dark matter, they are sensitive indicators of how these components behave. If you tweak the amount of dark energy in a simulation, the voids expand at different rates. If dark matter particles interact in some way beyond gravity, the structure of the cosmic web subtly changes. Cosmologists run countless versions of these universes with slightly different parameters. One with a faster expansion rate, another with a weaker gravitational constant, and compare them to real observations. The goal is to see which version of the simulated universe most closely matches the one we inhabit. This process is something like reverse engineering reality. Scientists start with theory, the equations that govern matter, energy, and space-time, and then let those equations play out in a digital cosmos. If the resulting voids and galaxy clusters line up with real ones, it's a sign that the theory is correct. If they don't, something in our understanding of the universe is missing. Voids, because they are so sensitive to the expansion of space itself, serve as one of the best benchmarks for testing these models. While galaxies and clusters tend to merge and grow, voids do the opposite. They expand and swallow smaller voids. Over billions of years, the empty regions merge like bubbles in foam, forming ever larger cavities separated by thinner and thinner filaments. This void hierarchy has been observed in both simulated and real data. The Boötes void, for instance, may be the result of several smaller voids coalescing over cosmic time, a process visible in simulations, but impossible to witness directly in real life. Running these simulations requires immense computational resources. Supercomputers like Summit at Oak Ridge National Laboratory or Frontier, the world's second most powerful as of the mid-2020 AS, can perform quadrillions of calculations per second. Yet even they struggle to simulate the entire observable universe at high resolution. Scientists often must choose between simulating a small region in great detail or a vast region with limited resolution. Despite these trade-offs, progress has been extraordinary. Modern simulations can now reproduce statistical properties of galaxy distributions, void sizes, and even subtle patterns in CMB distortions caused by gravitational lensing through voids. But building the universe in a machine also exposes its mysteries. When researchers adjust the value of dark energy or alter the initial density fluctuations, they find that certain combinations produce universes that look similar to ours, while others generate radically different outcomes. Some simulated universes fragment into too many small clumps, others collapse too quickly. A few expand so fast that galaxies never form at all. Somewhere in this enormous digital parameter space lies the delicate balance that produced our cosmos, and by extension, its great empty spaces. In several cases, simulations have predicted structures that were later observed. Before the discovery of the Sloan Great Wall, simulations suggested that galaxies could form enormous filamentary structures hundreds of millions of light-years long. Before the mapping of the Boötes void, they had already shown that enormous cavities should exist in between those filaments. Each time observations confirm these digital predictions, it reinforces the notion that our equations and our computers are accurately tracing the logic of the universe itself. The simulations are also helping scientists confront more speculative questions. Could voids harbor alternative forms of matter? Could the expansion of a void reveal something about the underlying geometry of spacetime? What happens if dark energy is not constant? By altering parameters and rerunning their models, researchers can explore these questions without waiting billions of years for the real universe to evolve. It is, in a sense, a time machine made of mathematics, one that allows humanity to glimpse both the past and possible futures of cosmic structure. Visualizations from these simulations are often breathtaking. The glowing filaments look like neurons, and the dark voids resemble synaptic gaps. Computational cosmology transforms nothingness into something tangible. By turning the invisible structure of the universe into data, it gives form to what once seemed beyond human reach. The voids within voids hypothesis. On smaller scales, voids contain subtle gradients, regions that are emptier than others, like pockets of air trapped within a larger bubble. When astronomers mapped the Boötes void in detail, they noticed irregularities, slight variations in density, and a few faint galaxy concentrations that didn't fit with a single uniform void. This hinted that it might be a composite, a merging of smaller voids that had expanded and fused over cosmic time. To visualize it, imagine a foam of bubbles pressed together. Each bubble represents a smaller void in the universe. Over time, the walls between some of these bubbles dissolve, merging them into a single, larger cavity. This analogy is remarkably close to how cosmologists now think large-scale structure evolves. In this view, the Boötes void is not an isolated feature, but a natural part of a hierarchical cosmic structure. A void made up of voids. Its vastness isn't the result of a single improbable event, but rather the cumulative effect of smaller voids merging, one after another, as the universe stretched and matured. Computational simulations have given this concept a solid foundation. In these simulations, small voids are common early on, appearing between dense regions as matter clumps. Over time, these voids expand and overlap. When they merge, their shared walls, thin sheets of galaxies and gas, collapse or fade, leaving behind a larger, emptier cavity. The Boötes void, then, could be the result of billions of years of cosmic evolution. Within a merged void, remnants of the original boundaries can persist, faint filaments or galaxy groups that were once at the edges of smaller voids. These remnants form faint ghostly threads across the darkness, subtle traces of the cosmic architecture that came before. The galaxies that inhabit the Boötes void might be the lingering remains of those dividing walls, marking where smaller voids once met. If the universe is built hierarchically, with smaller voids nested inside larger ones, then even the emptiest regions may contain hidden complexity. There could be layers of underdensity, subtle transitions and gradients that only become visible when examined with great precision. The Boötes void might appear uniform from afar, but within its expanse could lie faint structures, tenuous wisps of dark matter, rare intergalactic gas clouds and sparse galaxy chains, tracing the skeleton of vanished walls. If Boötes really is the result of many smaller voids merging, its formation timeline could reveal how quickly the universe expanded at different epochs. Some researchers have suggested that studying supervoids could even test theories of modified gravity, since these immense low-density regions are sensitive to the underlying physics that drives cosmic acceleration. When galaxy surveys are analyzed, voids tend to cluster hierarchically. The Boötes void, then, might be just one of the most extreme examples of this pattern. The concept of hierarchical voids also fits naturally into the mathematics of the cosmic web. Cosmologists describe structure formation using something called the Zeldovich approximation, a model that explains how initial density fluctuations collapse or expand under gravity. Smaller outflows can combine, creating larger expanding volumes. The result is a network of interconnected cavities, a hierarchy that matches what simulations and surveys reveal. Interestingly, this hierarchical structure doesn't just apply to voids. It mirrors the way galaxies and clusters form in dense regions. Just as matter builds up hierarchically, with small galaxies merging to form larger ones, emptiness seems to build up in the same way, with small voids merging to create supervoids. Comparing the giants, Boötes versus the giant void. When Boötes was first discovered, it was considered the largest empty region ever found. But then, astronomers stumbled upon something even larger, the so-called giant void. Found in the northern galactic hemisphere, this newer discovery would stretch our understanding of just how immense and intricate the structure of the universe can be. It forced scientists to question whether Boötes was truly unique, or merely one chapter in a much larger story of cosmic hollows that extend across the universe like the gaps between threads in a cosmic tapestry. The giant void spans an estimated 1.3 billion light-years across, almost 4 times larger than the Boötes void. It's located about 1.5 billion light-years away from Earth, in the direction of the constellation Hercules. This staggering size makes it one of the largest known structures, or rather non-structures, in the universe. It is so immense that if the Milky Way were placed at one end, light would take over 1 billion years to cross to the other. Despite the name giant void, it isn't completely empty. Like Boötes, it contains a sparse population of galaxies and filaments, but these are spread thin across an almost unfathomable volume. Astronomers estimate that its density is only about 10% of the average cosmic density, meaning it contains only a fraction of the matter found elsewhere in the universe. The discovery of the giant void came from observations of the CMB. In 2007, a team of astronomers analyzing data from the Wilkinson Microwave Anisotropy Probe, or WMAP, noticed what eventually came to be known as the cold spot. It puzzled researchers because it didn't fit easily with standard cosmological models. One of the leading explanations proposed that the cold spot could be caused by a massive supervoid. Subsequent studies confirmed the presence of a vast, underdense region aligned with the cold spot, now known as the giant void. In contrast, the Boötes void was discovered the old-fashioned way, through the direct observation of galaxies. It was a discovery born out of optical observation, not cosmic background data. This difference in how the two voids were discovered reflects the changing tools of astronomy. Boötes was found through painstaking cataloguing, the giant void through the subtle imprint it left on the radiation of the cosmos. Both reveal the universe's structure, but from entirely different perspectives. The giant void's relationship to the cold spot is one of the most intriguing aspects of its study. When photons from the CMB pass through it, they experience the integrated Sachs-Wolf effect. The giant void is large enough to produce this effect on a noticeable scale, making it one of the few cosmic structures that can visibly influence the universe's oldest light. Boötes, on the other hand, is not known to produce such a pronounced imprint on the CMB. Its distance and size, though massive, are not quite enough to distort background radiation in the same way. Instead, its scientific importance lies in its visible structure, its role as a window into how galaxies form and distribute themselves in vast underdense regions. In that sense, the two voids complement each other. Boötes shows us the visible emptiness of the universe, while the giant void reveals its invisible gravitational and energetic imprint. Comparing the two also highlights how voids can differ in shape and composition. The Boötes void is roughly spherical, giving it a more distinct boundary against surrounding structures. The giant void, however, appears less defined, more irregular, with a stretched or layered shape. Its uneven shape could be the result of multiple merged voids, just as Boötes might be, but on an even grander scale. Where Boötes is a bubble, the giant void is a vast cavity, not smooth but complex and ragged, reflecting the unevenness of cosmic evolution. Both voids also challenge the limits of our understanding of structure formation. In the standard cosmological model, the LCDM model, matter clumps together under gravity while empty regions expand. But there are statistical limits to how big a void should become over the universe's lifetime. The Boötes void already sits near the upper bound of those expectations. The giant void, however, pushes well beyond them. Its existence has led some cosmologists to wonder if our understanding of cosmic variance and dark energy might need refinement. How could such an immense underdensity form naturally? Was it a product of chance, an extreme statistical fluctuation? Or could it hint at something deeper, perhaps an early feature of the universe imprinted during inflation, the brief exponential expansion that occurred fractions of a second after the Big Bang? To understand the extremes these voids represent, it helps to think about their scale relative to the cosmic web. The observable universe is around 93 billion light-years in diameter. Within that vastness, most voids measure between 30 and 150 million light-years across. The Boötes void, at 330 million, already stands out. The giant void, at 1.3 billion, is almost on a different level entirely. So large it could contain multiple superclusters, like the Virgo and Laniakea superclusters, with plenty of room to spare. These sizes make them cosmological landmarks. The Boötes void contains around 60 known galaxies. The giant void's galaxy population is harder to measure, partly because of its distance, but it is likely even more diffuse. The galaxies that do exist within such regions are invaluable to astronomers. The giant void also raises questions about the influence such immense underdensities might have on the motion of nearby galaxies and clusters. In the same way that massive structures like the Shapley supercluster can gravitationally pull galaxies toward them, enormous voids can exert the opposite effect, a kind of gravitational repulsion due to their lack of mass. Some studies suggest that the giant void may contribute to subtle anisotropies in the large-scale flow of galaxies, meaning that galaxies in certain directions move slightly faster or slower relative to the cosmic average. The enigmatic KBC void. In 2013, 3 astronomers, Ryan Keenan, Amy Barger and Lennox Cowie, proposed a bold idea. They suggested that our own Milky Way galaxy might not sit in a typical patch of the cosmos, but rather within a vast underdense region. This immense region, now known as the KBC void, after their initials, would make our position in the universe unexpectedly special. It implied that, instead of living in a region of average density, we might be situated inside one of the largest known local voids. If true, it would subtly affect our measurements of cosmic expansion and possibly even our understanding of the universe's accelerating growth. The KBC void is thought to span nearly 2 billion light-years in diameter, centered roughly around the Milky Way and its neighboring galaxies in the local group. To imagine this scale, picture a sphere so enormous that it stretches beyond the Virgo supercluster, encompassing large parts of the Laniakea supercluster, the grand structure that contains our galactic home. In the model proposed by Keenan, Barger and Cowie, the density of galaxies and matter inside this region is lower than the cosmic average by about 20–30%. That might not sound like much, but on these scales, it's monumental. A void of that size and depth would influence how light travels, how galaxies move, and how the local rate of cosmic expansion appears to us. The idea emerged from observations of how galaxies are distributed across space. The researchers analyzed large-scale surveys of galaxies and found evidence suggesting that the number density of galaxies around us declines gradually with distance before rising again beyond about 300 million light-years. This pattern implied that we might be sitting in a sort of cosmic basin, a local underdensity embedded within a denser outer shell. The void, if real, would not be completely empty, but rather a gentle depression in the cosmic landscape, a region with fewer galaxies and less matter than average. To visualize this, imagine walking across a shallow valley. From your perspective, the horizon appears slightly elevated because the land rises around you. In a similar way, the KBC void would mean that the Milky Way resides in a subtle dip in the distribution of matter, surrounded by denser walls of galaxies. The light we observe from distant supernovae and galaxies would have to cross this uneven terrain of density, potentially distorting the measurements that cosmologists use to infer the rate of universal expansion. This is where the KBC void becomes especially interesting and controversial. One of the central puzzles in modern cosmology is the Hubble tension, the discrepancy between 2 different ways of measuring how fast the universe is expanding. Measurements made from the early universe using the CMB suggest a slower expansion rate. Measurements made from nearby galaxies and supernovae, on the other hand, indicate a faster rate. The difference is small, but persistent, about 5–10%, and has resisted explanation for years. Keenan, Barger and Cowie proposed that the KBC void might help explain this discrepancy. If we live in an underdense region, then locally, galaxies would be receding from each other slightly faster than the cosmic average. This is because, with less matter nearby to slow expansion through gravity, space would stretch more freely. To an observer inside the void, like us, this would make the local Hubble constant appear higher than it actually is on universal scales. In other words, the difference between local and cosmic measurements of the universe's expansion rate might not be due to new physics or exotic dark energy, but simply because of where we are located. It's a clever and elegant idea, but one that has met with skepticism. The main issue lies in the scale of the KBC void. To produce the observed level of Hubble tension, the void would need to be extraordinarily large and deep, far larger than what standard models of cosmic structure formation predict. A void nearly 2 billion light-years across is at the extreme edge of plausibility. Statistically, the odds of such a massive underdensity forming naturally in our region of the universe are exceedingly low. Yet, observationally, the evidence remains ambiguous. Some surveys, like the two M++ galaxy catalogue and the Cosmic Flows datasets, do show hints of a local underdensity, a region around the Milky Way that appears to have fewer galaxies and slightly faster expansion. However, other studies find that the effect is modest, not nearly large enough to explain the entire Hubble tension. It's a delicate balance between what is measurable and what is theoretically likely. The controversy also touches a deep philosophical nerve in cosmology, the Copernican principle, the idea that we do not occupy a special or privileged place in the universe. For centuries, this principle has guided astronomy from the dethroning of Earth as the center of the cosmos to the understanding that our galaxy is just one among billions. The KBC void challenges that intuition. If we happen to live in a region that is significantly emptier than average, then our cosmic vantage point is not entirely typical. That doesn't mean the universe revolves around us, but it does suggest that the local environment may be unusually distinctive. Some researchers have attempted to test the KBC void hypothesis by studying how light from distant galaxies is affected as it travels through space. If we live inside a large underdensity, light should experience slight changes in its redshift profile. Astronomers can model these effects using the Lemaitre-Tolman-Bondi, or LTB, solution, a general relativistic model that describes spherically symmetric inhomogeneities in the universe. These models predict that a sufficiently large void could mimic the appearance of cosmic acceleration, making the universe seem to expand faster locally than it does on average. However, when applied rigorously, most LTB models fail to fully reproduce the observed acceleration without invoking dark energy. They can account for some of the discrepancy, but not all. This suggests that even if the KBC void exists, it cannot entirely explain the universe's accelerating expansion. It might be part of the story, but not the whole. The cosmic acceleration still seems to require an additional ingredient, whether that's dark energy or some deeper modification of general relativity. One way astronomers continue to test the void hypothesis is through galaxy surveys that map the universe in ever greater detail. These maps reveal that while local underdensities exist, regions around 100 to 300 million light-years across, they tend to blend smoothly into the denser cosmic web beyond. If the KBC void exists as described, it would have to be much larger and more diffuse, making it challenging to distinguish from the natural gradient of galaxy density that already surrounds us. Even so, some researchers argue that we shouldn't dismiss the idea too quickly. Cosmic variance, the natural statistical variation in structure across different parts of the universe, means that not every region has to be exactly average. The universe, while homogeneous on the largest scales, can still contain vast fluctuations in density. If we just happen to occupy one of the slightly emptier regions that doesn't violate the Copernican principle, it merely places us in an atypical but not impossible location. The implications of the KBC void, if confirmed, would ripple across multiple areas of cosmology. It would affect how we interpret the local Hubble constant, how we model the CMB, and how we understand the distribution of galaxies around us. It might even alter our understanding of how cosmic voids evolve, whether they continue expanding faster than the rest of the universe, slowly evacuating themselves of matter, or whether they reach a stable equilibrium as dark energy dominates. Interestingly, the KBC void also forces cosmologists to reconsider the concept of local in cosmic terms. When we speak of local space, we usually mean our galactic neighborhood, a few million light-years. But in cosmology, Local can mean hundreds of millions, even billions of light years, because that's the scale on which matter and energy balance out. The KBC void, if real, redefines what we think of as our local environment. An enormous, faintly hollow region, encompassing everything we can directly observe with today's telescopes. Rather than being surrounded by a dense web of galaxies, we might be adrift in a sparse ocean, on the outskirts of the universe's great structures. The light we observe from beyond might be filtered through layers of underdensity and structure, subtly shaping the data we interpret. Our cosmic address, then, might be one of the universe's quieter, lonelier neighborhoods. The LCDM challenge: are we too centrally located? If the KBC void is real, it shakes the very foundation of how we think the universe is structured. The prevailing model of cosmology, known as LCDM, or lambda cold dark matter, assumes that on large enough scales, the cosmos is homogeneous and isotropic. That means, statistically, every region of space should look more or less like any other when viewed from a far enough distance. Galaxies clump together into filaments and clusters, but beyond a certain size, roughly a few 100 million light-years, those variations should average out into smoothness. The LCDM model relies on this assumption to explain the CMB, the distribution of galaxies, and the universe's accelerating expansion. But if we find ourselves near the center of a massive cosmic void, that assumption begins to falter. It introduces the uncomfortable possibility that our local environment is not representative of the universe at large. In the standard LCDM model, dark energy, represented by the Greek letter lambda, drives the accelerated expansion of the universe. Observations of distant supernovae in the late 1990s provided strong evidence for this acceleration, which led to the introduction of dark energy as a major component of the cosmos. But if we lived inside a huge, underdense region like the KBC void, galaxies beyond the void would appear to be receding faster than they truly are. Light traveling through denser regions slows slightly due to gravitational effects, while light passing through emptier regions can arrive with subtle differences in timing. These effects could mimic an acceleration in the expansion rate without requiring dark energy to be as dominant as currently believed. Astronomers have tried to test this idea using type Ia supernovae. If the local universe were significantly emptier, the apparent brightness of these supernovae would vary in ways inconsistent with the uniform expansion expected under LCDM. Early tests did not show such deviations, suggesting that if a local void exists, it's not large enough to fully explain the observed acceleration. However, the KBC team and others argued that subtle differences in data interpretation or biases in how samples are selected might be masking the effect. Even a slight underdensity spread over billions of light-years could have cumulative consequences for our measurements of the Hubble constant. The Hubble tension adds a new layer of intrigue. The LCDM model cannot easily reconcile it without invoking new physics or fine-tuning. Some cosmologists see the KBC void as a possible bridge between these conflicting measurements. If the Milky Way sits in an underdense region, the local Hubble constant would appear higher. This could partially explain why local measurements overshoot the cosmic average derived from the early universe. But many cosmologists remain skeptical. For one, the scale required for the KBC void to have a measurable impact is enormous, even by cosmic standards. The LCDM model predicts that such large and deep voids are statistically improbable. Galaxy surveys, while showing local underdensities, do not reveal an abrupt transition that would define a clear boundary for such a vast void. Instead, the universe seems to fluctuate gradually between slightly denser and slightly emptier regions, consistent with LCDM expectations. Yet there's a certain persistence to the KBC idea. It's not so much that cosmologists are eager to abandon LCDM, it's that the model, despite its successes, leaves lingering questions unresolved. The Hubble tension is one. The nature of dark energy is another. The uniformity of the CMB, contrasted with the lumpy distribution of galaxies, suggests that our local region could be an outlier in subtle ways. Even if the KBC void doesn't exist as a discrete structure, its concept represents a kind of scientific pressure point, a reminder that our understanding of large-scale structure is still evolving. Testing whether we live in a void requires precise mapping of galaxy distributions, CMB anisotropies, and peculiar velocities, the motions of galaxies deviating from pure cosmic expansion. Astronomers use instruments like SDSS and PanSTARRS to chart galaxy densities out to billions of light-years. Early data hinted at slight underdensities near our region, but not enough to classify it as a massive void. However, recent surveys have improved both coverage and depth, suggesting that large-scale anisotropies, irregularities in expansion or density, might indeed exist, even if they fall short of confirming the KBC model outright. The LCDM model assumes that the universe is best described by a Friedmann-Lemaitre-Robertson-Walker metric, which enforces large-scale homogeneity. If our region violates that assumption, cosmologists would need to adopt more complex, inhomogeneous models, perhaps ones that allow for variable curvature or anisotropic expansion rates. Such models can fit certain observations without invoking dark energy, but they introduce new parameters and often lack the predictive simplicity that makes LCDM so appealing. The notion of cosmic homogeneity is not merely a convenience. It's a belief that the laws of physics and the structure of space are the same everywhere. But what if that's only approximately true? What if our cosmic neighborhood happens to be statistically unusual, not unique, but rare enough to bias our measurements? The more we study cosmic structure, the more it resembles a complex hierarchy. From this perspective, a local underdensity might not be so shocking after all. It could simply be one layer in a vast self-similar cosmic web, a fractal-like pattern that only seems uniform when averaged over unimaginable distances. This doesn't necessarily break LCDM, but it may require refining how we interpret its predictions. If we are inside a modest void, for example, we might expect slight variations in observed Hubble flow, background radiation, and galaxy clustering compared to denser regions elsewhere. Detecting and quantifying those variations could help bridge the current gaps in cosmological measurements. Interestingly, this possibility brings us closer to the original spirit of the Copernican principle rather than violating it. If voids and overdensities are natural parts of the cosmic landscape, then our position in a relatively empty region is neither privileged nor coincidental. It's just one example among countless cosmic environments. What seems special may only feel that way because we're finally learning to map the universe at scales where such differences become visible. The apparent centrality within the KBC void may therefore be an illusion of perspective, just as Earth once appeared at the center of the cosmos before the heliocentric model revealed a broader truth. Still, the tension remains, both scientifically and emotionally. If the LCDM model is the grand architecture of the cosmos, the idea of a vast local void feels like a potential crack in its foundation. Yet cracks can also be opportunities, places where new ideas seep through, forcing us to re-examine assumptions that once seemed unshakable. Whether the KBC void turns out to be a defining feature or a data artifact, it has already served an important role. It has made cosmologists ask again not just what the universe is, but where we truly fit within it. And so, the mystery deepens, not only of the universe's structure, but of our place inside it. The more we measure, the more the data whisper conflicting stories. One suggests a smooth, elegant cosmos governed by equations that fit beautifully into theory. The other hints at subtle irregularities, vast, faint patterns that remind us that the universe may not be as uniform as we once believed. Cosmic flow and the great attractor. Everything is in motion. Galaxies, those immense islands of stars and dark matter, drift across the cosmic web like ships on invisible currents. To the human eye, the night sky feels eternal and unmoving, but over cosmic timescales, galaxies flow, pulled by gravity, pushed by emptiness. This movement, known as cosmic flow, reveals the hidden architecture of the universe. the places where matter gathers and the places where it vanishes. It is through this motion that astronomers have come to understand that space is not merely expanding, but also alive with gravitational tides that sweep across billions of light years. The Boötes void plays a subtle role in this grand motion. Immense voids push galaxies away, not because voids possess some repulsive force, but because they lack the gravitational pull of their surroundings. The universe, on its largest scales, is like a cosmic ocean made of both gravity and the absence of it. The discovery of these patterns began in the 1970s and 1980s, when astronomers first noticed that the Milky Way and its neighbors weren't just following the general expansion of the universe. They were also drifting at hundreds of kilometers per second toward a mysterious point in the sky. This motion couldn't be explained by the known mass of nearby galaxies. Something immense, was pulling us and thousands of other galaxies in the same direction. Astronomers called it the Great Attractor. The Great Attractor lies in the direction of the constellation Centaurus, hidden behind the dense dust of the Milky Way's plane, which makes it difficult to observe directly. Early attempts to map it relied on radio and X-ray observations that could penetrate the galactic obscuration. What they found was a vast region of enhanced density, stretching over hundreds of millions of light-years, centered roughly 150 to 250 million light-years away. This region contained galaxy clusters like Norma, Hydra, and Centaurus, each one a gravitational powerhouse in its own right. Together, their combined mass seemed capable of explaining at least part of our galaxy's motion through space. Yet even the Great Attractor was not the end of the story. As surveys grew deeper, astronomers discovered that beyond it lies an even larger structure, the Shapley supercluster. This enormous concentration of galaxies, roughly 650 million light-years away, is one of the most massive known structures in the local universe. The Shapley supercluster adds further gravitational influence, amplifying the flow towards it. The picture that emerged was of an intricate network of pushes and pulls, voids like Boötes creating outward pressure, while dense superclusters like Shapley create inward attraction. The motion of galaxies, including our own, results from the interplay between these cosmic giants. The cosmic flow, therefore, isn't a simple one-way drift. It's a dance between attraction and avoidance. When astronomers chart the motion of galaxies, they find streams and rivers of matter flowing along filaments, pooling into clusters and escaping from voids. The Milky Way, for instance, participates in what's called the local flow. Our galaxy, along with the Andromeda Galaxy and the rest of the local group, moves towards the Virgo cluster, part of the larger Laniakea supercluster. This vast domain, stretching over 500 million light-years, was defined by tracing the paths of thousands of galaxies and determining which direction their peculiar velocities, their motions beyond cosmic expansion, were pointing. All those motions converge toward the same basin of attraction. The Great Attractor sits within this gravitational landscape, forming a key node within Laniakea's boundaries. Astronomers cannot directly observe motion through static images. They infer it from redshift and distance measurements. A galaxy's redshift tells us how fast it's receding due to cosmic expansion. But to find out whether it's also moving relative to that expansion, being pulled or pushed by gravity, we must compare its distance to its redshift. If a galaxy is closer than its redshift suggests, it's likely being drawn toward us. If it's farther, it's being pulled away. When thousands of these measurements are combined, patterns emerge, invisible rivers of motion that wind between the walls and voids of the universe. The Boötes void, in this framework, acts like a low-pressure system in a gravitational weather map. Galaxies around its edges are subtly accelerated outward, their trajectories curving toward denser regions nearby. These outflows, though weak compared to the tugs from clusters, contribute to the overall cosmic flow field. They also help explain why matter in the universe tends to collect along filaments. The voids themselves shepherd it there by their very emptiness. In fact, cosmological simulations show that the expansion of voids can sculpt large-scale structure more effectively than collapse alone. As voids expand, they squeeze the surrounding matter into thin, thread-like boundaries. This interplay between attraction and expansion defines the universe's large-scale architecture. The Great Attractor and Boötes void are not opposites but counterparts, one dense, one empty, both essential to the balance of cosmic motion. Without voids, galaxies would not have clear paths to flow along. Without attractors, they would drift aimlessly in an expanding vacuum. Together, they maintain the subtle asymmetry that keeps the universe dynamic rather than static. Motion itself reveals more about the universe's structure than position alone. Galaxies may appear evenly distributed when viewed in isolation, but their movements tell a different story, one of imbalance and invisible gravity. The local group's motion of about 600 kilometers per second relative to the CMB is not random. It reflects the combined gravitational influence of both the voids and superclusters that surround us. In this sense, our journey through space is guided by a kind of gravitational current that has been flowing since the earliest epochs of structure formation. The Great Attractor, despite its name, is not a single object. It's a region, a gravitational well formed by overlapping clusters and filaments. When astronomers peer deeper, they find that the pull extends far beyond the immediate neighborhood of Centaurus and Hydra, linking to larger attractors like Shapley. Even beyond Shapley, the flow continues, hinting at vast, distant concentrations of matter that may still be uncharted. Meanwhile, voids like Boötes and the local void behind our own galaxy act as counterweights, influencing how galaxies migrate through this web. The universe, at its grandest scale, is governed by contrasts: light and darkness, matter and vacuum, attraction and repulsion. The cosmic flow represents a kind of cosmic respiration, a slow and silent breathing of galaxies over billions of years. Clusters inhale, drawing matter in; voids exhale, pushing it outward. If our galaxy is caught in a region of space where the flow is dominated by nearby voids and attractors, then our observations of redshift, luminosity, and distance could carry subtle biases. Light from distant galaxies bends, stretches, and shifts through the uneven gravitational landscape, just as sound changes pitch when it travels through moving air. Correcting for these effects requires detailed mapping of both local and large-scale flows, a task that continues with modern surveys like Cosmic Flows 4 and DESI. Each new map brings the invisible structure of motion into sharper focus. If we could watch this dance unfold across cosmic time, if we could fast forward billions of years, we would see the web itself evolve. Voids would swell, merging into larger caverns. Clusters would collapse further, sharpening their gravitational grip. The Great Attractor might fade as new attractors emerge farther away, while the Boötes void continues to expand, hollowing out a larger region of cosmic space. Every galaxy, including our own, is a traveler in this immense and ongoing flow. The role of dark energy in expanding nothingness. If dark energy is everywhere and acts uniformly, one might expect its influence to be the same in all regions of space. Yet, cosmic voids provide a unique testing ground because of their extreme emptiness. Within a void, there is little matter to resist the stretching effect of dark energy. Galaxies are sparse, gravitational wells are shallow, and the space between things is freer to expand. That means voids could, in theory, expand faster than the universe as a whole. To visualize this, imagine inflating a balloon dotted with small patches of tape. The taped spots represent clusters of galaxies where gravity holds matter together tightly. The rubber between them represents the voids. As the balloon inflates, the rubbery voids stretch more than the taped regions because there's less resistance. Over time, those empty areas dominate the balloon's surface, just as cosmic voids increasingly dominate the volume of the universe. This analogy captures one of the subtle truths about cosmic evolution. It is not just galaxies moving apart, but the empty regions between them expanding more rapidly than the rest. Astronomers can study this process through the motion of galaxies at the edges of voids. galaxies near the boundaries of large, underdense regions tend to be gently pushed outward, as if sliding down a slope away from the void's center. This provides direct evidence that gravity and dark energy are working in opposite directions. The deeper the void, the stronger the outward flow. By measuring these motions with precise redshift surveys, researchers can estimate how fast voids are growing, and from that, infer the strength of dark energy's repulsive effect. Although Boötes contains some galaxy filaments, its interior is dominated by space that is almost pure vacuum on a cosmic scale. If dark energy acts uniformly, one might expect Boötes to be an exaggerated version of the universe's general expansion, a place where the accelerating effect is more pronounced. Simulations suggest that such voids not only expand, but also help drive nearby galaxies toward dense clusters, effectively amplifying the contrast between emptiness and matter. Over billions of years, this process may cause the cosmic web to become even more pronounced. Dense filaments connected across vast chasms of nearly perfect void. But there's a deeper reason scientists are so interested in voids when studying dark energy. Unlike galaxy clusters, which are influenced by complicated gravitational interactions, voids offer a relatively clean environment. Their simplicity makes them ideal laboratories for testing cosmological models. If we can measure how fast voids expand, how their shapes evolve, and how their surrounding galaxies move, we can check whether those behaviors match the predictions of LCDM. Some models predict that the rate of void expansion should depend on the equation of state of dark energy, essentially the ratio of its pressure to its density. In LCDM, this ratio is fixed at -1, meaning dark energy behaves like a constant property of space itself. But if observations of voids were to show faster or slower growth than expected, it could imply that dark energy is not constant, that it changes over time or interacts with matter in unexpected ways. Such a discovery would rewrite one of the most fundamental assumptions of modern cosmology. Surveys record the positions and velocities of millions of galaxies, allowing researchers to identify the largest underdense regions and measure their properties in detail. By comparing these observed voids with predictions from simulations, cosmologists can place new limits on dark energy's behavior. What they've found so far is intriguing. In many observations, voids appear to be slightly larger and emptier than LCDM predicts, though the uncertainties remain large. Some analyses suggest that the apparent excess growth could be due to dark energy's dominance, while others think it might reflect differences in how voids are defined or how galaxies trace the underlying dark matter distribution. Yet even these ambiguities are valuable because they highlight how much information lies hidden in the universe's quietest regions. The relationship between dark energy and voids can also be seen through their imprint on the CMB, as previously discussed. In a universe without dark energy, CMB photons passing through voids would gain and lose equal amounts of energy. But because dark energy causes those potentials to decay, the photons lose a little extra energy, producing a measurable cooling signature. Thus, both the shape of voids in galaxy maps and their fingerprints on the CMB provide independent ways to test the same cosmic phenomenon. Some cosmologists have gone further, suggesting that voids might even act as natural amplifiers of dark energy's effects. If dark energy density truly remains constant as the universe expands, then the relative importance of dark energy compared to matter increases as matter becomes more diluted. Inside voids, where matter is already scarce, that dominance happens sooner and more strongly. In other words, a void might be a miniature version of the universe's far future, a place where dark energy has already won the cosmic tug-of-war. Studying how those regions behave today could therefore provide a preview of what the entire cosmos might look like billions of years from now, when galaxies are so far apart that most of the universe is effectively a single, expanding void. But not all theories of dark energy predict the same thing. In some alternative models, such as quintessence or phantom energy, dark energy is not constant but dynamic, evolving over time or varying across space. In those cases, voids could expand differently depending on when and where they formed. Detecting even subtle variations in the expansion rates of different voids could help distinguish between these models. That's why cosmologists are now using machine learning and massive computer simulations to track the evolution of tens of thousands of voids across simulated universes, comparing their statistical behavior with what telescopes actually see. There's an almost poetic symmetry. The most mysterious energy in existence, one that cannot be detected directly, that does not emit light or exert force in any ordinary sense, might be best studied through the universe's most silent, empty spaces. Supervoids become cosmic magnifying glasses. Their very emptiness allows dark energy to express itself unopposed, stretching space in a way that may hold the key to understanding the ultimate fate of everything. If dark energy continues to dominate, the future will belong increasingly to the voids. Over billions of years, galaxies will drift apart faster than gravity can pull them back together. Filaments will thin, clusters will dissolve, and cosmic structures will fade into isolation. In the end, the universe may come to resemble a single vast void, cold, dark, and ever-expanding. The Boötes void, then, is a glimpse of what the universe is becoming. Hidden structures. Could there be matter we can't see? Even in the darkest regions between galaxies, there are always faint traces of matter. Gases stretch so thin that a single cubic meter might contain only a few atoms, particles of dust adrift for billions of years, and invisible threads of dark matter weaving quietly through space. The Boötes void, for all its size and isolation, is almost certainly no exception. The question is not whether there is anything there, but whether we have the tools to see what little remains. Over the past few decades, the sensitivity of our instruments has grown exponentially. Telescopes can now detect galaxies so faint they barely emit a whisper of light, and radio observatories can trace wisps of hydrogen gas that stretch across millions of light years. Yet, even with such advancements, vast parts of the sky remain underexplored. The Boötes void's interior is one of those regions where our cosmic maps still fade into uncertainty. If a few galaxies could survive in such an underdense expanse, perhaps there were many more below our detection limits. Small, dim systems that current telescopes simply cannot see. Dwarf galaxies, for instance, can be thousands of times fainter than normal spiral galaxies, and at distances of hundreds of millions of light-years, they could easily vanish into the background noise. If most of the matter inside a void takes forms that do not shine, our picture of cosmic emptiness might be more about our limitations than about the universe itself. This is why cosmologists often distinguish between galaxy voids, defined by visible structures, and matter voids, which include dark matter and gas distributions. The two are not always the same. By analyzing gravitational lensing distortions statistically, researchers can map out where mass exists, even in regions devoid of visible galaxies. So far, large-scale surveys show that voids do contain dark matter, but in significantly smaller amounts than the cosmic average. The filaments that pass near them appear to thin out, but not completely disappear. This means that the Boötes void is likely not a total vacuum, but a faint shadow of the cosmic web, where only the lightest traces of matter remain. Another clue comes from hydrogen, the most abundant element in the universe and the last remnant of the primordial gas clouds that filled the cosmos after the Big Bang. Using radio telescopes, astronomers can detect the faint emission from hydrogen's 21-centimeter line. In some voids, long tendrils of hydrogen have been found connecting isolated galaxies, almost like invisible umbilical cords of cosmic material. These connections suggest that voids are not sealed off from the rest of the universe. Instead, they may be the quiet corridors through which diffuse matter still flows, slowly feeding or draining galaxies along their edges. The Boötes void might therefore host a network of these invisible filaments, too faint for current instruments. Simulations of large-scale structure formation predict that even in the emptiest cosmic regions, thin strands of dark matter and gas should persist, They act as bridges, maintaining the skeleton of the cosmic web even where galaxies have failed to form. Detecting such features, however, is enormously difficult. The densities are so low that even the most powerful telescopes, like the Square Kilometre Array under construction, would struggle to detect them directly. Instead, researchers rely on stacking data from many voids or using statistical correlations to infer their existence. There's also the question of whether voids might contain exotic forms of matter. Some theories propose that dark matter could clump differently depending on its particle nature. If dark matter consists of WIMPs, it should follow the overall structure of the cosmic web. But if it's made of something like axions, hypothetical ultralight particles, it could form diffuse waves or halos that subtly alter how light passes through a void. Detecting these differences could provide clues not only about the contents of voids, but about the fundamental composition of the universe itself. Another intriguing possibility is that voids might harbor faint, low-temperature plasma left over from the reionization era. Some simulations suggest that as the universe expanded, small pockets of intergalactic plasma became trapped in low-density regions, forming diffuse clouds that still persist today. These clouds could emit weak X-rays or distort the light of distant quasars in measurable ways. Observatories like Evacuation and future X-ray missions may one day detect such emissions, providing a glimpse of the last hidden matter in places like Boötes. Understanding what fills this emptiness is essential for a complete picture of cosmic evolution. The total amount of baryonic matter in the universe still doesn't match what cosmological models predict. About half of it is missing, unaccounted for in stars or galaxies. Some of it likely hides in the thin gas between galaxies, especially in the outskirts of clusters and inside voids. The Boötes void, with its immense volume, might contain a significant fraction of this missing matter, too diffuse to see, but enough to tip the balance of cosmic bookkeeping. As detection technology advances, astronomers expect to find more within the darkness. It may turn out that the Boötes void is not a pure void at all, but a thinly populated, fragile structure, a shadow of the cosmic web that remains visible only to those who know how to look. Perhaps faint dwarf galaxies drift silently along its invisible filaments. Perhaps diffuse gas clouds wander, heated only by the weak radiation of distant quasars. Perhaps even dark matter forms ghostly patterns we have yet to map. Voids as cosmic laboratories for physics beyond the Standard Model. The Standard Model of cosmology is our best description of how the universe works on the largest scales. It rests on two pillars: Einstein's general theory of relativity, which describes how gravity operates, and the existence of dark energy. Together, they produce a model that fits most of what we see. But, as mentioned, there are hints that this picture might be incomplete. One class of models, known as modified gravity theories, proposes that Einstein's equations might need tweaking on the largest cosmic scales. Another category suggests that dark energy might not be a cosmological constant at all, but a dynamic field. These ideas are incredibly hard to test in ordinary settings. But in voids, the balance between matter and energy is so delicate that even the smallest change in the underlying physics could produce measurable effects. Some analyses show that the growth rate of cosmic structure within voids doesn't perfectly align with our predictions. If confirmed, that would mean that the fundamental constants of physics might not be constant, that the rules governing space and time subtly shift depending on how empty or filled a region is. Some theoretical frameworks already entertain this possibility. For example, chameleon gravity models propose that gravity's strength depends on the local density of matter. In dense regions like galaxies, gravity behaves as Einstein described, but in empty regions like voids, an additional force emerges. Another idea, fifth force theories, suggests that new, previously undetected interactions operate over cosmic distances, hidden from view, except in places where normal matter is scarce. If a modified gravitational effect exists, its influence would accumulate over hundreds of millions of light years. potentially producing measurable distortions in how galaxies on its edges move. Researchers have used the Boötes void as a model in simulations that incorporate different dark energy behaviors or alternative gravity theories. They track how these changes would alter the void's shape, the alignment of surrounding galaxies, and the patterns of light traveling through it. Beyond gravity, voids also provide unique environments to test how light interacts with space. In dense regions, light is constantly deflected, absorbed, or distorted by matter. But in voids, photons travel across immense distances almost untouched, making them excellent tracers of the universe's geometry. The CMB, for instance, can be used to study how light from the early universe is influenced by voids it passes through. If dark energy behaves differently inside voids, it could alter the gravitational potential in subtle ways, changing how the CMB's photons gain or lose energy. Measuring these shifts helps refine our understanding of the universe's large-scale structure and the forces shaping it. Could the Boötes void be an ancient scar? There's an idea, still on the edge of cosmology, that the great empty regions scattered across the universe may not just be accidents of gravity, that perhaps some of them are fossils from a time before galaxies, before stars, even before matter as we know it condensed from the primordial fire. To some scientists, Boötes almost looks like a scar, a cosmic indentation carved into the very structure of space-time itself, left behind by something ancient and violent that took place long before our familiar universe ever came to be. The story begins during cosmic inflation. This was the universe's most extreme growth spurt. According to standard inflation theory, these fluctuations were random, distributed nearly evenly across space. But some cosmologists have wondered whether something more dramatic might have happened. Events that didn't just create tiny ripples, but vast imbalances, perhaps even collisions between entire regions of the inflating universe. Inflation isn't necessarily a single, uniform process. Many versions of the theory predict a multiverse, a collection of bubble-like universes, each one forming as inflation ends in a slightly different way. If two of these expanding bubbles ever collided, the impact would leave a lasting imprint on the structure of space-time. The collision might distort the distribution of matter, alter the local geometry of the universe, or leave behind a region with slightly different physical properties. Some researchers have suggested that enormous cosmic voids could be the remnants of such ancient collisions, the scars where two patches of the inflating universe once met and disrupted each other. In this speculative view, the Boötes void could be one of those scars. Its vastness and unusual emptiness would then be not the result of galaxies drifting apart over billions of years, but rather a primordial defect, a zone where the energy field that drove inflation behaved differently, perhaps cancelling out density fluctuations or wiping away potential matter before it could ever form. In that case, the Boötes void would be older than any galaxy, older even than the CMB. It would be a surviving footprint of whatever processes shaped the birth of the cosmos. Physicists call these hypothetical remnants cosmic textures or topological defects. They're predicted by certain high-energy theories that try to unify the fundamental forces of nature. During the first microseconds after the Big Bang, as the universe cooled, it underwent a series of phase transitions, shifts in its underlying fields similar to how water freezes into ice. If those transitions didn't occur perfectly smoothly, imperfections could form, knots, walls, or void-like regions where the energy field failed to align with its surroundings. These defects would then evolve over cosmic time, perhaps stretching or dissolving as the universe expanded. A large enough defect might leave behind an immense underdense region, something that, tens of billions of years later, we would see as a void. If a void truly originated from a primordial event, it would have certain distinctive signatures. For example, it might produce a circular or symmetric pattern in the CMB, a cold ring or hot ring, where the collision altered the temperature of photons passing through that region of space. Scientists have already looked for such patterns in the CMB, hunting for what they call bubble collision imprints. Some analyses have found faint, suggestive anomalies, ring-like cold spots that could, in theory, correspond to past cosmic collisions, though none have yet reached the level of proof. The Boötes void, located relatively nearby in cosmic terms, is harder to link directly to the CMB since it formed long after the radiation we observe today was emitted. Yet, its existence still provokes similar questions. Could the underlying region of spacetime where Boötes lies have been influenced by an early universe defect? Could its expansion rate or geometry carry traces of some primordial asymmetry? Its sheer emptiness, with so few galaxies scattered across such a huge volume, remains strikingly unusual. That statistical unlikelihood keeps the door open to deeper, more exotic possibilities. Some versions of inflation theory, particularly those involving multiple energy fields rather than a single one, naturally produce regions that differ dramatically from one another in density. These fields might interact in complex ways, leading to the formation of false vacuum bubbles, regions where the energy density was temporarily trapped in a higher state before collapsing. When these bubbles decayed, they would release bursts of energy, expanding rapidly and leaving behind imprints in the surrounding space. If such a decay happened unevenly, it could carve out an enormous underdense zone, a kind of void seeded by the physics of inflation. In this context, the Boötes void might be a fossilized boundary between two phases of the early universe. One can imagine, for a moment, the universe less than a trillionth of a second old, a boiling froth of quantum fields, fluctuating wildly as inflation tears space apart faster than light could ever travel. Within that chaos, two bubbles of the inflating vacuum brush against each other. Their boundaries distort, sending waves of energy rippling outward. Most of the scars vanish in the ongoing expansion, but one, by chance, remains imprinted in the density field. Billions of years later, galaxies condense everywhere else, yet this patch, smoother, emptier, scarred, becomes what we now call the Boötes void. Of course, this vision is speculative in the extreme, but science advances precisely by testing such daring ideas. To evaluate them, cosmologists look for patterns that ordinary void formation cannot explain. For example, if the Boötes void were the result of a bubble collision, the galaxies around its edge might show an unusual degree of symmetry, as if shaped by a single spherical disturbance rather than a chaotic gravitational evolution. The gravitational potential inside the void could also deviate subtly from what general relativity predicts. Even the polarization of the CMB in the direction of the void could carry hints of a primordial impact. So far, observations have not confirmed any of these features, but the tools for testing them are rapidly improving. If a void like Boötes contains any trace of an ancient topological defect, it might subtly alter the lensing of light from background galaxies. Detecting that would be like finding a faint fingerprint of an event that happened when the universe was less than a heartbeat old. Inflation was driven by fields of energy that operated at scales far beyond anything achievable in laboratories. If voids can reveal traces of those fields, they become windows into the realm of the untestable, offering a rare experimental handle on the physics of the Planck era. Was the Boötes void once filled? If we imagine the Boötes void as the endpoint of billions of years of matter outflow, it becomes conceivable that it might once have contained far more galaxies than it does today. However, if galaxies were indeed pulled away from this region, the question becomes, where did they go? The edges of the Boötes void might hold the answer. Observations show that its boundaries are lined with a faint but noticeable wall of galaxies. Some cosmologists believe that these walls may represent the accumulated matter that once occupied the void's interior. As gravity gradually tugged at galaxies within Boötes, their paths may have curved outward, spiraling toward these denser zones, leaving behind a near-total vacuum in the center. In this view, the void's walls are the visible record of the migration that carved out the emptiness within. Such a process would take billions of years. Galaxies move at hundreds of kilometers per second relative to one another, but even at those speeds, Crossing a void the size of Boötes would take longer than the current age of the universe. Yet gravitational influences extend across vast distances, and the process doesn't need to involve every galaxy moving far. Even subtle redistributions of mass, with galaxies sliding slightly toward neighboring filaments, can cumulatively hollow out large volumes. The Boötes void might thus represent a region where gravity's long, patient influence has acted almost perfectly, pulling away just enough matter to leave behind one of the most dramatic examples of cosmic evacuation ever seen. Still, not everyone agrees that the Boötes void must have been emptied over time. Some argue that it might have been born this way. These two explanations aren't mutually exclusive. The early universe's initial unevenness could have given Boötes a head start as a region of relative emptiness, while subsequent gravitational processes amplified that difference. But if galaxies were once more common there might be faint evidence of their past, traces too dim to see but not entirely erased. Astronomers have searched for such traces in several ways. One approach involves studying the faint light that permeates the void, the so-called extragalactic background light. This diffuse glow represents the cumulative radiation from all galaxies and stars throughout cosmic history. If the Boötes void were once more populated, some of that ancient light might still linger, scattered by intergalactic dust or faint streams of gas. Sensitive instruments like those aboard the New Horizons spacecraft and the Hubble Space Telescope have attempted to measure subtle differences in background brightness across different regions of the sky. While no definitive variation has been found that aligns perfectly with the Boötes void, these searches continue to refine our understanding of whether complete emptiness is even possible. Another clue could come from the void's internal galaxies, the lonely few that remain. By studying their properties, astronomers can infer how long they've been isolated. If they show signs of having interacted with other galaxies in the distant past, or if their shapes suggest tidal stretching, it could imply that they were once part of a denser environment before being left behind. Some of the galaxies within Boötes do indeed appear peculiar, irregular in form, dim and poor in gas. They might be the remnants of an older generation that survived the gravitational evacuation, fossils of a once more crowded landscape. Their existence doesn't prove that the void was ever full, but it hints at a long history of quiet evolution, galaxies stranded as the rest of their cosmic neighbors drifted away. Since dark matter dominates the mass of the universe, its distribution determines where galaxies form and where they don't. If dark matter in this region flowed outward due to surrounding gravitational imbalances, it would take normal matter with it. This process would effectively evacuate both visible and invisible components of the void, creating a region doubly empty, lacking not only galaxies, but also much of the dark scaffolding that typically underpins them. Simulations of cosmic flows suggest that such migrations of dark matter are possible, especially when influenced by large neighboring clusters. If the Boötes void lies between several massive superclusters, it could be the result of their combined gravitational push, gradually sweeping matter out of the region over cosmic time. Every void exists because something else doesn't. The matter that was once within it didn't disappear. It went somewhere else. This redistribution gives rise to the web-like structure of the universe. Where we see emptiness, others see the consequence of fullness elsewhere. The walls surrounding the void, glowing with clusters and superclusters, might represent the places where Boötes' lost matter came to rest. Some have proposed that Boötes might have experienced something like a collapse of its internal structures. In this view, galaxies within the void could have fallen into surrounding filaments, leaving behind only the faintest traces. This is a natural process in the evolution of the cosmic web. Not all regions form galaxies at the same rate, and some lose their gravitational cohesion altogether. A galaxy adrift in an underdense region might find itself slowly drawn outward, merging with distant structures over billions of years. If enough such events occur, an entire volume of space could become nearly devoid of galaxies without any dramatic cataclysm. just through the cumulative flow of time and gravity. Voids teach us that the universe is not static but fluid, shaped by endless motion and redistribution. Whether Boötes began as an unusually quiet patch of space or became one over eons, its existence shows the power of gravitational contrast, how the same force that builds galaxies can, in other regions, unmake them. The Boötes void may well be one of the most dramatic examples of this fading. If galaxies once drifted through this space, their light long extinguished, or their paths bent outward by the pull of distant clusters, their absence today speaks of the universe's restless balance. New surveys, new maps, the age of precision cosmology. Even now, with tens of millions of galaxies catalogued, our cosmic cartography remains incomplete. Much of the universe's structure lies beyond the reach of our current instruments, faint, distant, or hidden behind the glow of closer stars. But that is beginning to change. A new generation of observatories is preparing to redraw the cosmic map with a precision never before possible, transforming the study of voids into a high-definition science. The upcoming era of precision cosmology will be defined by missions like Euclid and the Vera C. Rubin Observatory, each designed to probe the universe's large-scale structure in unprecedented detail. Together, they will not only reveal new galaxies, but also expose the vast patterns that connect and separate them, the invisible web of matter, dark energy, and gravitational influence that shapes everything. For the first time, we may be able to see the cosmic voids not as isolated gaps in data, but as coherent, evolving entities, the dark spaces between the luminous threads of the cosmic web. The Euclid Space Telescope, launched by the European Space Agency, is among the most ambitious of these efforts. Orbiting beyond Earth's atmosphere, Euclid's mission is to map the geometry of the universe by observing how galaxies and dark matter are distributed across more than one-third of the sky. Using both visible and near-infrared light, it will measure the shapes and distances of billions of galaxies, allowing scientists to detect the subtle warping of light caused by weak gravitational lensing. This distortion will not only trace the locations of massive clusters, but also reveal the contours of cosmic voids, where lensing is weakest. For researchers studying Boötes and other voids, Euclid's data could be transformative. It will show, with unprecedented clarity, how light bends as it travels through emptiness, how even nothing can leave a measurable signature on the universe's structure. While Euclid surveys the heavens from space, DESI on Earth is conducting its own groundbreaking census. Mounted on the Mayal telescope in Arizona, DESI is designed to measure the redshifts of over 40 million galaxies and quasars, effectively mapping how far away each lies from us. The result will be a three-dimensional model of the cosmos so detailed that astronomers can trace its expansion, its clustering, and its voids across more than 10 billion years of history. By combining redshift data with gravitational lensing observations, DESI will allow scientists to identify thousands of new voids, measure their sizes, and track how they evolve over time. More than ever before, researchers will be able to test the predictions of cosmological models like LCDM, not with a handful of massive voids like Boötes, but with a statistical sample large enough to probe the very nature of dark energy. The precision of DESI's data, measuring galaxy positions with an accuracy of fractions of a percent, means that even small discrepancies could reveal cracks in our understanding of fundamental physics. Then there is the Vera C. Rubin Observatory, perched high in the Chilean Andes. Unlike Euclid or DESI, Rubin's power lies in its time domain, its ability to repeatedly scan the sky and capture the changing universe in motion. Using its 8.4-meter mirror and massive 3.2 gigapixel camera, the observatory will photograph the entire southern sky every few nights, collecting tens of terabytes of data each session. Over a decade, this survey, the Legacy Survey of Space and Time, or LSST, will catalogue billions of galaxies, revealing faint structures and extending our reach into the distant universe. What Euclid and DESI measure in depth and redshift, Rubin will provide in breadth and temporal richness. For cosmic voids, this means the chance to see not just where they are, but how they subtly change, how the distribution of matter within and around them evolves as the universe ages. One of Rubin's unique contributions will be identifying ultra-faint galaxies, those hidden populations that may inhabit the edges of voids or drift alone in their centers. These galaxies, often invisible to earlier surveys, could reveal how star formation persists in the most isolated environments. If voids like Boötes still contain pockets of faint matter, Rubin will help bring them to light. Its repeated imaging will also improve the accuracy of photometric redshifts, crucial for constructing three-dimensional void catalogues. With this data, scientists can cross-reference Rubin's observations with Euclid's and Deci's, layering them into a complete multi-dimensional map of the universe. Beyond these flagship projects, other instruments will add their own perspectives. The Nancy Grace Roman Space Telescope, NASA's next major space observatory, will complement Euclid's work with even deeper infrared imaging, enabling finer measurements of cosmic acceleration and dark energy. The Square Kilometre Array, a massive radio telescope network being built in South Africa and Australia, will map the universe in neutral hydrogen, tracing the faint radio glow of hydrogen atoms across cosmic time. By revealing the structure of matter at different wavelengths, these observatories will build a composite picture. As the data pour in, cosmologists will enter an era where statistical precision replaces cosmic guessing. Until recently, studying voids meant focusing on a few dozen large examples. Now, scientists expect to catalogue tens of thousands of voids across the observable universe. These will range from small local pockets only a few million light-years wide to gargantuan depressions spanning billions of light-years. With so many examples, researchers can begin to classify them systematically, comparing their shapes, densities, and environments. Patterns might emerge. Perhaps voids form in predictable hierarchies, or their sizes correlate with cosmic age or local matter density. With better statistics, what once seemed like exceptions may turn out to be the rule. One of the major goals of these surveys will be to refine the void power spectrum, a mathematical description of how voids of different sizes are distributed throughout the universe. Just as the clustering of galaxies tells us about dark matter and cosmic expansion, the distribution of voids offers complementary clues about what drives the universe's growth. By comparing how voids expand at different epochs, scientists can measure how dark energy's influence has changed over time, potentially distinguishing between a cosmological constant and more exotic possibilities like dynamic scalar fields or modified gravity. Voids also offer a way to test the assumption that the universe is homogeneous. If surveys reveal systematic variations in void sizes or densities across different regions, it could challenge one of the most fundamental principles of cosmology. The precision of Euclid, Deci, and Rubin could confirm or rule out ideas, like the KBC void, helping to determine whether the cosmos truly behaves the same in all directions. But perhaps the most exciting aspect of this new era is its unpredictability. Every time astronomy has improved its vision, from Galileo's telescope to Hubble's Space Observatory, it has overturned expectations. When the first large-scale surveys were completed in the late 20th century, they revealed a universe far more structured and interconnected than anyone had imagined. Now, as instruments probe deeper, the next revelation might come from the spaces between galaxies. These surveys will also serve as a bridge between observation and simulation. With high-resolution data on void shapes and growth rates, theorists can test their computer models against reality, refining their understanding of the universe. Already, cosmologists use large-scale simulations. Yet no simulation can be trusted until it's checked against the universe itself. The upcoming maps will provide that check, allowing scientists to see whether their virtual universes match the one we inhabit. The next generation of simulations. In the past, astronomers worked with pencil sketches, equations, and rough statistical models. The cosmos had to be imagined, a mathematical construct that could only be compared loosely with telescope observations. But in the 21st century, That imagination has come alive. Now, the most powerful supercomputers on Earth can recreate the entire history of the universe. They allow us not only to look back in time, but also to test ideas that no telescope can yet confirm. The newest generation of simulations has reached a level of complexity and detail that would have seemed impossible only a few decades ago. Early models could track a few thousand or perhaps a million particles, too few to capture the fine texture of cosmic structure. Today, supercomputers handle trillions. Each particle in these models doesn't just represent a single atom or star, but vast swaths of matter, both visible and dark, whose behavior collectively follows the laws of physics. By allowing these particles to interact under the influence of gravity, expansion, and radiation, researchers can watch the universe build itself step by step. The result is a living replica of the cosmos, galaxies that cluster, filaments that stretch, and voids that open like cosmic lungs breathing across the eons. Among the most ambitious of these simulations is Illustris T-Eng, the successor to the original Illustris project. Run on some of the world's most powerful supercomputers, it models a volume of space nearly 1 billion light-years across, with over 20 billion resolution elements representing dark matter, gas, stars, and magnetic fields. When visualized, its virtual universe looks strikingly similar to the real one seen in large-scale surveys, long filaments connecting knots of galaxy clusters, surrounding vast cavities of near emptiness. Within these cavities, the simulation reveals not complete vacuums but delicate gradients of dark matter and faint streams of gas, the hidden scaffolding that shapes void evolution. By comparing such simulations to real observations, scientists can check how well their models reproduce reality and adjust the underlying physics accordingly. As simulated universes evolve, voids begin as tiny, underdense patches in the early matter distribution, growing larger as gravity pulls surrounding material into denser filaments. But the rate at which they grow depends on the properties of dark energy and dark matter. The Millennium simulation, once the largest of its kind, laid much of the groundwork for this field. Though it lacked baryonic matter, it was one of the first simulations to show how voids could emerge naturally from gravitational dynamics. Since then, newer simulations have added more ingredients to the cosmic recipe. They now include hydrodynamics, the motion of gas, as well as the effects of star formation, supernova explosions, black hole feedback, and even magnetic fields. Each of these factors subtly alters how matter flows through space, especially in the low-density environments of voids. For example, feedback from supermassive black holes in distant galaxies can heat surrounding gas and drive it outward, seeding nearby voids with diffuse matter. Similarly, the collapse of large-scale filaments can create pressure waves that push against void boundaries, shaping their contours. By capturing these effects, simulations are beginning to show how interconnected every part of the universe truly is. Even the emptiest regions are influenced by forces born in the densest galactic cores. A great power of modern simulations lies not just in reproducing what we already know, but in predicting what we have yet to observe. In these digital futures, voids continue to expand while clusters grow denser, creating sharper contrasts between something and nothing. If dark energy remains constant, this process will accelerate. Galaxies will drift farther apart, filaments will thin, and voids will dominate ever more of the universe's volume. Eventually, the cosmic web will become ghostly. These simulations give us a glimpse of that distant epoch, showing how emptiness will one day rule the cosmos. Other models go even further back in time, rewinding the universe to its earliest moments to see how the first seeds of structure were planted. In these primordial simulations, density fluctuations are drawn from the tiny ripples seen in the CMB. By comparing the statistical properties of these simulated voids with those observed today, cosmologists can test whether our universe's early conditions match theoretical expectations. The computational power required to run such simulations is staggering. The largest runs occupy thousands of processors for weeks or months, performing quadrillions of calculations per second. These machines, often housed in government or university research centers, generate petabytes of data, enough to fill entire data centers with digital universes. Each frame of these simulations represents millions of years of cosmic time, and visualizing them requires specialized software capable of handling vast amounts of information. When rendered in color and motion, they reveal the beauty of the universe's structure. In the near future, these simulations will become even more sophisticated. Artificial intelligence and machine learning are being integrated to help analyze the enormous datasets they produce, identifying patterns and anomalies far faster than humans can. AI algorithms can scan through thousands of simulated voids to classify them, track their evolution, and even predict what unseen structures might lie beyond the limits of current telescopes. In effect, the machines are teaching themselves how to read the language of cosmic structure, translating the silence of voids into data we can interpret. One day, simulations and observations may converge so tightly that we can describe the universe's evolution from its first microsecond to its last trillion years with near-perfect precision. In that future, the great voids, Boötes, the giant void, the KBC, will no longer be cosmic mysteries, but essential chapters in the story of everything. Through the lens of computation, emptiness becomes a teacher, showing us the ways in which the universe's vastest silences are filled with meaning. Which other wild structures of the universe would you like to hear about? Sound off in the comments below, and if you enjoyed the video, consider leaving a like and subscribing. Thanks for watching.